With another live. Let me show you how my water's already boiling. And over here is Baji. And over here is Suji. Good evening, good morning. It is Monday night. Well, early hours. Hi, Fuji. Fuji is like, well, if the live is starting, I'm gonna take a nap and I'll be ready for a snack later. Fuji Baba. Fuji Baba, you can stay here for the live. That's Baji's favorite toy right there. We are back with another live, and this time I've got my tea going already. So I am looking forward to seeing many of you joining the live. Welcome, welcome. Thank you for being here. Welcome to the live. And also, thank you for being here if you're seeing this as a video upload later on. Most welcome, and we will hang out for a bit here. And thank you for being here. So we have been covering a bunch of physics topics in the subfield lately of cosmology. So we have been covering cosmology recently. I'm going to see what people are interested in today and take a look. So let me first look at my, let me first share the live, and then we'll take it from there. So let's see, is everything showing up on the live? And also let me do this. Let me do the thing where I move a bit closer. It's a, oh, actually, I have to get up. My tea is almost done. So, welcome, welcome. If you are joining, thank you for being here. Look at our iPad cover. Looks like a lab notebook. Thanks to my dad for getting me this. Hello, welcome. How are you? Hello, everybody. Wait a minute. Can I click on my own live or not? If you've already gone to bed, sorry about that. Ooh, there. Hi. Hello. It is I, Baji the handsome cat. Baji's mom. Baji will soon join me on my lap, I'm sure, as soon as I make my tea. So, okay. Hi, welcome. Hi, James. San Antonio, Texas. Very nice. Yay. I've been into San Antonio. What did I say? San Antonio? I've been to San Antonio, Texas. I've been to Lackland, Ramazan Guler. Hi, how are you? Thank you so much for joining the live. Welcome, join us and chat, please. And we will discuss some topics here soon. Let me share the live on my community tab. We are live. Yay, welcome to everybody. Hi, James. Hi, Ramazan. Hi, everybody. Thank you. Hi, Ramazan. Gozelson. I'm not sure what that means, but thank you. Okay, so soon we will start our topic. I might go get my tea though. Okay, I shared the live. I will pin this message. If anybody else wants to chime in, then yeah. Feel free to say hi in the chat. Thank you for being here. Okay, so we have been talking about cosmology recently. This is a cats and books and physics kind of channel. It's mainly, you will see a lot of the videos and shorts have kitty cats in them. So thank you so much for watching our videos and shorts and also coming to the live stream. We really appreciate you. Oh, really? Thank you. Oh my gosh. Hammerhoid Nibbler, my family and I really enjoy your channel. Keep up the hard work. Thank you so much. Thank you, Hammerhoid Nibbler. I'm so glad to hear that your family is enjoying the channel. So what we mainly have been discussing during these live streams is a ton of physics topics. And lately we have been talking about cosmology and what cosmology, sorry about that, what cosmology means, how it's kind of different from astronomy versus astrophysics and particle physics. We also spent a lot of time a few lives ago, probably through November mainly, we talked a lot about Einstein's work and pretty much the 20th century modern physics. And we referenced this book called Einstein's Cosmos by Michio Kaku to give you this sort of information in a more digestible manner. So it's a more accessible science communication for these topics, especially for modern physics. That's mainly relativity and quantum mechanics, especially in the 1900s, 1910s, 1920s, 1930s type of timeline. And then later on in the 1900s, like closer to 1980s, 1990s, those type of things are a little bit more considered the more current topics that we're getting into now. So basically, after kind of looking at relativity and quantum mechanics, we took a look at some astrophysics topics as well. And I also mentioned that in the universe right now, after this great background that we already have from the live streams of November, where we understand modern physics from the 20th century, really the biggest questions that are pending right now for us to solve is number one is dark energy and number two is dark matter. Some people might even consider those flipped. Maybe dark matter is more important to them and dark energy is less important. But both of those are very important questions, open questions right now. And actually, there is even a third open question. I would say the top three open questions are dark energy, dark matter, and number three is the origin of elements. Now, even though what we are made of, us human beings, cats, trees, planets, comets, this is all ordinary matter or baryonic matter, one might even say baryonic matter plus electrons. What we are ordinarily matter made of is, wait, let me make sure that I didn't miss a comment. Okay, I think I just can't read that last comment, sorry. The elements that are in the periodic table, basically a lot of those elements we kind of understand how they were made. Most of them are made in stars. When the universe first started, and soon after the universe came to be after the Big Bang, there was mostly just hydrogen and a little bit of helium and very, very small amounts maybe of lithium, and pretty much all the other elements above helium have to be made in stars. So we know that elements are made in stars, and for a lot of them, we actually understand pretty well the type of environment, the type of process in which they're made. But there are still some elements that we don't fully understand. So that's what I mean by the third question is origin of elements. Sorry, sometimes it takes a bit longer for me to say what I'm saying. And so the third question, when I say origin of elements, it's not that we don't know how the elements are made, all of them, but we just don't know how some of them are not made, how some of them are made. We just don't know exactly, or we haven't confirmed exactly the process for which some of them are made. But something like up to iron, or even some of the more heavier elements above barium, we understand pretty well how they're made in stars. Anyways, so some people like to include origin of elements in the top three questions, obviously because it is such a, it's such a fundamental question. So out of all the fundamental, biggest, most open questions right now are, again, dark energy, dark matter, and origin of elements, with the origin of element caveat being that we do understand many elements, how they're made, but there are still some that we don't quite understand. I'll mention one. I think it is molybdenum. We don't quite understand how molybdenum is made, depending on who you talk to, especially for within nuclear astrophysics and fields like that. So those are our current physics or current research type of open questions. So these would be what you would work on if you would go into the field, or they could be. Those are some of the biggest questions really that you would work on. You could also work on, there are also some other questions, of course. These are some of the biggest open questions. Pretty much everything else, those are totally fine too. Like I worked on neutrino particle astrophysics, and I mentioned before that the neutrino is a particle that we understand better now. It's a lepton. It's in the same family of particles in particle physics as the electron, but it's not very much like the electron. It's just in that family, but in many ways it's very different as well. And it was lesser known. It's more of a more recent, last 20, 30-year thing that now we understand so much more about the neutrino particle. So I worked on that. And in fact, when we talk about dark matter and we started to look at the astrophysics angle of looking at dark matter, because the dark matter question can be approached in a few different ways. I mentioned in some of my lives that sometimes you can approach it in an astrophysicsy kind of way, astronomy kind of way, or you can approach it in a particle physicsy kind of way, or you can approach it in a cosmology kind of way. So right now we've been covering more of a cosmological approach, or a cosmology. What is cosmology? What is the universe, large scale perspective on dark matter? Why we need dark matter? What is the approach of a cosmologist when it comes to dark matter? What is its importance? What is the motivation? In other words, too, like, because if dark matter wasn't so important in, say, for example, structure formation in the universe, because we found in cosmology, just as a quick tidbit, that the distribution of galaxies in the universe is not a random distribution. There is some sort of structure there, and so it turns out that dark matter might be important in that structure. So now cosmologists are going to be interested in understanding what dark matter is. Of course, we don't understand what it is. We don't know what it is. There are lots of ongoing efforts to find out what it is. But I wanted to tell you about the different types of motivations. So if from the astronomy or astrophysics approach, astrophysics astronomy is more specific. It's more to do with, say, a specific object in the sky, a specific event in the sky, or our own galaxy, our galactic center, the supermassive black hole in the galactic center, our neighboring galaxies, the sun. I mean, sure, some people like the sun, So, I mean, the sun is good, but maybe not the most interesting, depending on, again, who you talk to. So those things are more astronomy and astrophysics. And then there's the universe, which is more of a cosmology type of thing. So we saw that even within our own galaxy, this is a very concerning, perturbing matter, this dark matter topic. We found this came up. How it came up in astronomy or astrophysics is because we discovered that the way we thought things should be was not how things were. So in other words, there's the galactic center, and we're going around the sun, and the sun is going around the galactic center, and we're around 8 kiloparsecs from the galactic center. And we kind of know where most of the stuff, or so we thought, we kind of know where most of the ordinary matter in the galaxy is. It contributes to the luminosity. And we expected that the orbital speeds of things that are far away from the galactic center will be slowing down. But in fact, or becoming constant or something, it would follow what we expected the things would do when most of the mass is closer to the galactic center. But we found there was a rotation, there's a curve, actually, I showed it in a previous live stream, that the orbital speeds were not only not slowing down, they were kind of increasing. So now we had this thing about where we actually, there was this extra matter that we didn't know that there was, even in our own galaxy. So that's an astrophysics problem. When astrophysicists look at our own galaxy and they kind of understand, okay, this is what's contributing to the mass of the galaxy because that's where the luminosity is, all of the things that contribute to the stuff that's, giving us brightness, luminosity, that should be the mass. And we know it, but then we find out that we don't know it, then that's a dark matter problem in terms of our own galaxy. And we found that this is also the case. Even some neighboring galaxies have this issue where there might be, dark matter might be playing a role there. But then we also saw that, so this particular proof that I talked about, this evidence of dark matter with the orbital speeds as a function of distance from the galactic center. This is a curve that people show all the time when they talk about dark matter evidence, because some people might not still believe that this is a problem, right? So this is the astrophysics problem. Then there's also cosmological problems with, for example, dark matter. Even in the topic of dark matter, cosmologically, unfortunately, we also need it. So this is where it has really gained. Come, Suji, college pe. This is where it has really gained significance and gotten further motivation, because now we're seeing that we have come up with sort of ways to calculate how each thing in the cosmic inventory contributes to the critical density of the universe. So a long time ago, when Einstein was writing down his equations for general relativity, we covered this in the previous live streams when we talked about his work, but basically he gave us the more updated, more correct theory for gravitation, right? Because Newton had given us gravitation way back when, and that is still valid for the most part when you are within classical realms. Classical mechanics, classical physics is still correct. NASA still uses it to launch spacecrafts. But when you go into relativistic fields, when you might want to understand cosmic scales, then you might want an updated theory of gravitation, and that is provided to us by Einstein. He worked on it after he gave us special theory of relativity in 1905, and he realized that, well, we need not just inertial physics of the inertial frames or non-accelerating frames, but we also want physics of accelerating frames or gravitating frames. So we got general theory of relativity, which is now the updated, up-to-date theory of gravitation. But when he's writing down the equations for the universe, he's realizing, oh my gosh, well, if everything was just gravitation in the universe, then the universe would collapse, but it has not collapsed. So I must stabilize it with something. And he introduced a parameter, and he called it the cosmological constant. This is something that we talk about even 100 years later in the form of dark energy. So that's a different thing. It is this energy of the vacuum, this energy that's working against gravity. And Einstein had reluctantly introduced it to accommodate a stable universe. But it turns out that the universe is not only stable, it is expanding, and its expansion is accelerating. These are things that we have now confirmed much later after his general theory of relativity came out. So that all makes it even more interesting. And now, at this time, when we take a cosmic inventory and we think about the universe from its birth, from Big Bang to where it is now, we understand that it has gone through some changes, and it has gone through evolutions. And the content and the look and feel of the universe is not the same as a function of cosmic time. It has changed. And we introduced this concept of a scale factor, A, small a, as a function of time, cosmic time, small t. And we showed that in the beginning of the universe, it was very radiation dominated, or photons dominated light. Photons were the king of the jungle in the beginning times, in the early universe. Then the universe cooled down, and things started to happen more. Like back when it was radiation dominated, you didn't have neutral atoms and things like that. Those could not form. When things are so hot, you need things to be able to cool down to levels of like EV for like look up the ground state of the hydrogen atom, right? It's like in EVs. So you can't do that when things are so chaotic and hot and excited, right? So the moment you're trying to become an atom, some photon is hitting you in the face and you can't, right? So so it was radiation dominated, and the universe's behavior was different. Then we actually even collected on some of these older photons from when the universe was of the baby age of only 300,000 years old, and it's called the cosmic microwave background. And we saw it's actually very homogeneous, very smooth looking, very everything is in equilibrium, because there's not much for these photons to have done before they are now coming to us from that very old time, right? So they look very smooth. That gives us the early universe. You might hear people say is very smooth as in this is what I mean. It looks homogeneous. There's not a lot of when they looked in the beginning, especially they thought that it's not got a lot of inhomogeneity, but actually now, not now as in later on, because this was back in the, I think it was like 30 years ago, 40 years ago, when the CMB was first discovered or first started to get measured. So after like 25 years of research, people started to actually notice that there are some perturbations around the smooth universe. There might actually be some inhomogeneities in that smooth universe, and which might actually give us explanation for some other details of the universe. But anyway, when we take a cosmic inventory now of what all the things we think there are in the universe, now that it's 14 billion years old, and we have collected a lot of data. We have collected, we specifically collected data to figure out whether the universe is expanding, and we saw that it was in fact expanding. So now all of that taken together, and we went into this in depth last night. The cosmic inventory is as follows. Okay, what's in the universe? Cosmic inventory. Number one, it's photons. There's definitely photons. There's definitely light particles. Number two is baryons. And the author that we have been referencing, Scott Dodelson, he wrote Modern Cosmology. He lumped together baryons is basically neutrons, protons, but he lumped together electrons as well. So it's fine, whatever. Baryons is number two. So photons first, baryons next. And then he gave us something called matter density, which is basically now saying that other than baryons, there's this other type of mass as well, which we find when we look gravitationally. So we call it dark matter because it's not baryonic matter. And then number four, neutrinos, and number five, dark energy. So those are the cosmic inventory. There's just 5 types of things, and 3 of them we understand. So we just got to figure out the other 2. So, so again, 5 types of things in the cosmic inventory: photons, baryons, dark matter, neutrinos, and dark energy. So just 5 things. Dark energy is the 5th thing, quintessential thing, and we don't know exactly what it is. There's research going on to figure out what it is. And we also don't know what is dark matter. As in, what is the particle nature of dark matter? What is it really? There have been dark matter candidates. I mentioned one. Neutrinos were considered at first to be dark matter candidates. Some things are subjective. Which thing are you saying is subjective? So the fact that we need that we have something called dark matter is now proven from different angles. I mentioned about the astrophysics evidence. There's also cosmological evidence. We covered this last night, actually for a couple nights now. I think I mentioned it the night before too. I forget because I go live on most nights. So I think for a couple of lives now we've been talking about cosmology mainly, and we have a lot of evidence of dark matter from cosmology. And in fact, we have a better estimate and percentage of exactly what content of the universe is dark matter because we have a good understanding of the baryonic density of the universe. Hi. So let me actually do that, redo that part. I'll give you a little tidbit from the book here. Because, so this is very interesting. It's so interesting because baryons are neutrons, protons, and electrons, right? These are all things that interact with light. So, yeah, okay, I understand what you're saying now. Okay, great. Yeah, so neutrons, protons, and electrons all interact with light. So when we say that I measured some baryons, it could be that like these measurements are, it's not a single measurement, right? It's not like somebody took one measurement once and that's it. Like there, it's generally many types of measurements that are taken over time by many different organizations and people and things like that. So, so some of the evidence we talked about last night was actually the light way of figuring out the baryons. Like this one. Let me read this. So we're calling this big omega B. So the baryonic matter density is big omega, and subscript B is the baryonic density. So the simplest way is to observe the baryons today in galaxies. The greatest contribution to the density, though, comes not from stars in galaxies, but rather from gas in groups of galaxies. So this is another thing we mentioned last night. So it's not actually the stars in galaxies that give us the most baryons. It's actually the gases in these galaxies. Galaxies have a lot of gas as well, and those have a ton of baryons. In these groups, this big omega subscript B, hi Baji, is about 0.02. So now we're taking an inventory of the baryonic density in the universe with the help of these galaxies. The second way to count baryons is by looking at the spectra of distant quasars. So this is not just the galaxy data now, we're also looking at distant quasars. The amount of light absorbed from these beacons, so quasars are, hi, excuse me, thank you, Baji. Quasars are beacons of light. The amount of light that's absorbed from these quasars is a measure of the intervening hydrogen. So if you if you identify some quasars and then you want to measure the light that's coming from these quasars, the amount of light absorbed from these quasars is a measure of the intervening hydrogen. And I should mention, even now, the most abundant element in the universe is, guess what? Hydrogen. Everything else is much less. So in the universe, I know on Earth it's a little different, but in the universe overall, the most abundant element of the universe is still hydrogen, okay? So, and hence the baryon density. So this is the quasar way of getting the baryon density. Two ways now, galaxy way and quasar way. These estimates, and this is from 1997, so you can look up this paper if you'd like, Rauch et al., R-A-U-C-H, in 1997 suggested that the omega small b h to the 1.5 is around 0.02, where h is the Hubble constant, I believe. Yes, it's Hubble constant. So with a fairly large uncertainty. So there was a big uncertainty on this, but they came up with 0.02. A third method is to infer the baryon density by careful scrutiny of the anisotropies in the universe. So I mentioned about the smooth universe because of the photons, but there are some anisotropies in that smooth universe. As we will see later on in chapter 8, we're on chapter 2 now, these depend on the baryon density. Preliminary studies from 2001, another study from 2001, put the density of that baryonic density to 0.024-ish from the CMB. So looking at the cosmic microwave background, which is mostly smooth, and looking for some of the anisotropies and doing some study of it, and then trying to get an estimate for the baryonic density from it, because baryons were going to be a lot less back then. When the universe is only 300,000 years old, that CMB radiation, that's from the photons. So, but it would have some anisotropies. So getting some estimate from that gave us 0.024. Finally, we see in chapter 3 that the light element abundances are sensitive to the baryon density, and that estimates of these abundances pin down the baryonic density to around 0.0205. So remarkably then, these estimates of the baryon density with very different techniques. So they're all very different techniques that we have just mentioned now, 3 or 4 different techniques that we mentioned just now to measure the baryonic density of the universe. They all agree more or less. It's around 0.02, basically. They all place the baryon density at roughly 2 to 5% of the critical density. And that is the critical density of the universe. We're trying to understand the content of the universe in terms of its critical density. What each thing contributes to this critical density. So baryons is contributing around 2 to 5% according to this, all these things we just said, to the critical density. The total matter density in the universe is higher than this, so there must be matter in the universe that is non-baryonic. So we'll get into that now. But basically, this baryonic density we just talked about, this is the normal matter stuff. This is ordinary matter. This is protons, neutrons, and electrons. And, in terms of hydrogen pretty much in terms of the stuff where hydrogen atoms are getting, are absorbing light, that's most of the abundance of the, most of the elemental abundance in the universe is hydrogen atoms. So that's what that is. But there's some other ways too that they've calculated this. I have a question. What do you think about subtonic particles? I don't know what that is. I have to look it up. Hey Google, what is a subtonic particle?
According to Wikipedia, in physics, a subatomic particle is a particle smaller than
Hey Google, can you pause? So Google heard it as subatomic. Subtonic. Yeah, I don't know.
Sorry, I don't understand.
That's okay. So baryonic density, which is just neutrons, protons, and electrons in this particular chapter, because electrons is not really baryons. Strictly speaking, electrons are fermions or leptons. But for this particular calculation, the author has lumped them together. Ordinary matter made up of... Are we good? Okay, I think we're good. Yes, okay. I'm looking at my Wi-Fi thing. It's not blinking. Okay. So now we will consider other ways of understanding how much matter there is in the universe. So we're still taking a we're still basically taking a we're still basically doing bookkeeping. We're doing an accounts. That's what I meant. Subatomic. Oh, yeah. I have a question. What do you think about subatomic? Yeah, of course. Yeah. So real quick, we just covered baryonic matter density in the universe, which is neutrons, protons, electrons in this part of the book. Even though electrons are strictly speaking not baryons, they're fermions or also sometimes called leptons. Let's quickly cover all the particles. So particle physics gives us 3 families of particles, roughly speaking. These are leptons, quarks, and bosons. Okay, so what I think about subatomic particles, I'll just tell you what I know about all the particles. And so these are, again, leptons are something like the electron is an example of a lepton. Sometimes it's also called a fermion. In quantum mechanics, there is this property called spin, and depending on the spin of the particle, of the fundamental particle, sometimes it gets a category based on that. But also in particle physics, there's roughly these 3 types of particle families, and these are leptons, quarks, and bosons. So under leptons, we basically have something like the electron is a lepton, something like the neutrino is also a lepton. So electrons and neutrinos are in the lepton family. Electrons and neutrinos are in the lepton family. Neutrinos are very different from electrons, though. Neutrinos are, sometimes I call them the much lighter cousin of the electron. They're much more low mass, and they also don't have a charge, and they also don't
don't interact with the electromagnetic fields. They interact through the weak force. So their interaction is different. The bosons that they exchange with each other is different, because we'll get to the third type of particle, which is boson. Quarks are what make up neutrinos. Quarks are what make up neutrons and protons. So the second type of particle is quark, little quarks. As an example, there are other types of quarks too, but the protons and neutrons are subatomic particles that are not fundamental in the sense that they further break down to quarks. And then lastly, the third type of particle is, good. The third type of particle is bosons, and an example of bosons is photon, light. Another example of boson is the W boson or the Z boson. There are other bosons. Basically, the forces, so how particle physics kind of explains it, that is that the forces are carried, through bosons. For example, a photon is the boson that carries the electromagnetic force. The W and Z bosons carry the weak force. So that's it. Those are all the particles that we know of. There may always be more particles that we discover. We still don't know the particle nature of dark matter. We don't know the particle nature of gravitation. Some people call it graviton, but I don't know that it's been discovered, at least not to my knowledge. I can only mention the ones that we list as well as we have discovered, and these are leptons, quarks, and bosons. So those are all the particles, basically. Sometimes other people will have different names, like just now I mentioned baryons, right? This is a cosmology term. So I've mentioned how some of the subfields of physics will have slightly different terminology and will call things differently, right? So don't get them confused. Basically, everybody understands protons, neutrons, right? So I'm just gonna say baryons, nothing special. They're just protons and neutrons, right? Just pretty much just the elements, basically. That's the baryons. Some elements have neutrons, some don't. Like the hydrogen atom just has a proton. So when you say neutrons and protons, well, most of those most of the protons can also be just called hydrogen atoms, depending on whether the electron is there or not, whatever. But if you're strictly just interested in the mass, then the electron's mass is a lot less, right? So whatever. So neutrons and protons are called baryons, sometimes collectively by cosmologists. We just looked at the baryonic density in the universe as a whole because we wanted to take inventory of the cosmos, like cosmic inventory. It's a question in cosmology that we're pursuing at this time, in this book, in this discussion. In terms of particles and how people call them, in particle physics, people call things either leptons, quarks, or bosons. I'll just mention again that sometimes, depending on the spin, some people also called certain leptons fermions. Electron would be an example of that. So that's what that is, okay? So that was a real quick overview of particle physics. We'll come back to the matter density of the universe because we started this topic. Basically, we kind of got an estimate for baryonic density of the universe, and we saw that it's contributing to like 5% at most of the 5% at most of the critical density of the universe. So is that all? Is that all there is to matter? So now we will consider some other methods of measuring matter. All of the methods of measuring the baryon density mentioned so far involve the interaction of matter and radiation. So we actually took into account the matter that interacts with photons, right, in order to measure those things. For example, simply counting stars works at some level because we roughly know how much mass is required to output the light from a typical star. Because again, by knowing the luminosity, we will know about the mass. There are, however, methods, and luminosity is a light, right? So that's like basically using light to understand how much mass there is. And it's very nice in astronomy. See, this is an astronomy-y type of thing. In astronomy, uh, as hard as astronomy can be sometimes to do, because the objects of interest are generally very far away, but we also know clever things like the mass of an object, and the luminosity. These are the mass of a star is very important. Pretty much once you know the mass of something, you'll know like its entire life. So we've covered also in previous live stream about stellar remnants, how stars die and what they become into. And pretty much we mentioned that depending on the star's mass, you'll know whether it becomes either a white dwarf or a neutron star or a black hole. So pretty much we are very good with luminosity, associating luminosity and mass with other knowledge in astronomy. So yeah, we know. There are, however, methods of measuring the mass of matter that do not rely on the way light and matter interact. And this is going to be very important now. These classically have involved measuring the gravitational field in a given system, thereby inferring information about the mass responsible for that field. So we have some inferred mass to light ratios of many systems. Over here, we will look at it, ranging from galaxies to superclusters. Historically, this ratio, so getting the mass to light ratio of things like galaxies and superclusters, at first you're not going to have a complete list, right? It's almost like you're working on the list as you go. So historically, this ratio was measured on small scales first, suggesting that the density in the universe was far less than critical. So, at first the measurements were simply not complete. We just didn't do all of them or didn't do more of them. As more large-scale data were obtained, the steady increase in the mass over light ratio led some cosmologists to speculate that eventually we would find that the density was critical. Bacall and collaborators in 1995 and 2000, there are 2 papers here, however, have argued that mass to light ratios do not increase past R of around 1 megaparsec. A leveling off occurs consistent with a matter density of around 0.3, where omega m, this is big omega, small m, as in the entire matter density. And remember how the number we said earlier was around 0.02-ish? This is now omega m, as in all of the matter density, is around 0.3, where omega m is the ratio of the total matter density today to the critical density of the universe. So basically, they found that this omega m thing is like 0.3, which is a lot more than 0.02, right? Okay. Recently, a number of other techniques for inferring the matter density have emerged. We will see in chapter 7 that the distribution of galaxies in the universe, this is what I was talking about earlier too, is that the distribution of the galaxies in the universe is not random. So we will see that the distribution of galaxies in the universe, in particular the power spectrum of this distribution, is very sensitive to omega m, the matter density, the total matter density. So this is going to be of a huge interest to people who want to understand the structure formation in the universe. So when the universe, after it was born and did its thing, early universe, all that, and then it started to form structure. Like, at first we didn't have stars. These old first stars started, forming, galaxies started forming. The way the universe evolved, right? At first we didn't have stars. We didn't have galaxies. So slowly, at different epochs, basically, of the universe, this is happening. And now that we look at the distribution of the galaxies in the universe, after we collect more and more data, it's not random. There is a structure to it. And people want to understand that structure. People are asking what's driving that. And it turns out that it's very sensitive to this total matter density. Virtually all galaxy surveys have inferred this matter density thing to be 0.2. So not 0.02, but 0.2. So another number. So we're collecting numbers now. We will bring it all together. Another cosmological probe, we will... Another cosmological probe we will encounter later on in chapter 9 is the cosmic velocity field and its relation to the observed galaxy distribution. These are related by the continuity equation, a relation sensitive also to matter density. Again, most of the measurements are clustered around a matter density of 0.3. So this is another thing. And this also gives us a matter density of around 0.3. So we've got something like 0.3 from some places, 0.2 from some places, and we'll bring it all together. Another way of measuring the total mass density is to pick out observations sensitive to omega B over omega M, so the baryonic over matter density ratio, and use the apparent value of omega B to infer the matter density. For example, most of the baryonic mass in a galaxy cluster is in the form of hot gas. So we mentioned that most of the stuff in a galaxy cluster is actually hot gas. It's not, most of the mass is not in stars, but in hot gas. The ratio of the mass of gas in clusters of galaxies to the total mass can be measured either by looking for X-ray emission, we have a paper from 1993 there, or by looking at the electron-heated CMB in the direction of the cluster. We did this in 2001. If this ratio is characteristic of the universe as a whole, and it probably is because clusters are so large, then the cosmic baryon to matter ratio is around 20%. Since baryons make up only about 5% of the critical density, the total matter density is inferred to be about 25%. Another way, so these are all the ways, another way of inferring the baryon to matter ratio is by looking for features in the power spectrum of galaxies. If the baryon fraction is truly of order 20%, then there will be wiggles in the spectrum. So this is, again, we'll check this later on in chapter 7 here. There are tentative hints of these wiggles in the early data from the 2-degree field, and these pin down the baryonic to the matter density to around 0.15, consistent with the cluster observations. Finally, the anisotropies in the CMB are sensitive to the matter density, which is the omega matter. Recent determinations indicate that this omega matter thing is 0.16 from 2001. So we have all these different numbers now. Given the fact that current best estimates of the Hubble constant, the small h, is 0.72, the CMB observations also are consistent with a matter density equal to 30% of the critical density. So from all these different various estimates and things like that, hi evil green dog, we get 30% is the matter density total. Yes, I think, yeah, something like that. We therefore have an enormous amount of evidence telling us that the baryon density is of 5% of the critical density, while the total matter density is some 5 times larger. Most of the matter in the universe must not be baryons. It must be some new form of matter, which is dark matter. So that's the cosmological inference and view on how and why we need dark matter. There's also astrophysics evidence, astronomy evidence. This is the cosmology evidence. Okay? A to the 4 due to the stretching of the universe and wavelengths causing cosmic expansion. Oh, nice. Are you talking about the perturbation? Are you talking about the scale factor? Because it's it a to the 4 or a to the, do you mean a to the 3? But yeah, that's why we need dark matter, or that's why even cosmologists basically are saying that we have dark matter. We need dark matter in order to account for the matter density in the universe. We're discussing cosmology. We're discussing the dark matter perspective, the cosmology perspective of dark matter, and how dark matter is motivated in cosmology. And we found that the baryonic density is only 5%. It's at most 5% of the critical density, whereas dark matter is something like 20% of the critical density. So there's a lot more dark matter than there is ordinary or baryonic matter. And dark matter is non-baryonic. It's not made of neutrons, protons, electrons, stuff that we know about and stuff that we're made of. So then, naturally, after people discovered the neutrino, another type of particle, and also realized how neutrinos are really elusive, they're weakly interacting. Guess what? Another particle that does not interact with photons and does not interact with the electromagnetic field is neutrinos. So when people first learned about, oh my gosh, like there's this matter, bookkeeping gone wrong, there's this non-baryonic missing matter, people immediately, the natural suggestion was that it might be neutrinos. So so people thought that, oh my gosh, is there just a mega frick ton of neutrinos that we've missed, which is actually dark matter? So both in astrophysics, we read it from the astrophysics book too, but an initial an initial dark matter candidate that was being proposed by astrophysicists and even cosmologists. So I read it from this book as well, which is a cosmology book. It's Modern Cosmology by Scott Dodelson. Maybe Scott Dodelson is in the chat right now. Hi, Scott, if you're here. Hi. So, but basically, these people too, the cosmologists too, thought that neutrino might be the dark matter candidate. And that's because, Baji, and that's because, don't bother Suji, baby. And that's because, why? Because neutrinos are elusive, they don't interact much, they're weakly interacting, but there's one big issue with the neutrinos, they're very low mass. So in astrophysics, in the astrophysics book that we read, we also saw this, that they thought that neutrinos might be a pretty good dark matter proposal, but they were too low mass. And in fact, that kind of might have motivated some people to think about, like, what if, like, they imagined up, like, the neutrinos are too low mass. What if we imagine up something that's kind of like the neutrino, but more massive, so that it can account for all this missing matter, which is the dark matter? So they came up with this thing called WIMP, which is the weakly interacting massive particle, which is basically like the neutrinos, but more massive. So that's another, again, candidate for dark matter. So now we've discussed two candidates for dark matter. So why we're calling these candidates is because there is nothing confirmed about dark matter. There's only constraints, I'm sure, in papers that come out on this research, but dark matter is not confirmed. So anything when I say dark matter, it's a dark matter candidate. And most neutrinos are now discarded for the most part. They might contribute some fraction of the missing matter, but for the most part, they're not thought to account for dark matter. But good guess though, good guess. You can imagine why they would have thought that neutrinos might be dark matter. So then the next candidate is the WIMP, weakly interacting massive particle. These are kind of like the neutrino, but more massive. And there are experiments that are looking for this. And this is why I think it's funny. Like, I worked on a neutrino experiment. So if you worked on a neutrino experiment, you might be pretty good at also doing dark matter experiments, because they might have some similarities, right? Depending on, because they're both elusive particles. Not that we know what the dark matter particle is, but I guess that they're pretty elusive because doesn't interact with photons. So some of the techniques that might come in handy in a neutrino observatory or neutrino detection type of experiment might also translate over to the dark matter experiments. I think they do. And there are efforts ongoing in astronomy, astrophysics, and particle physics, because that's sort of the cross-section in which neutrinos are also lying, depending on which neutrino you're interested in detecting. whether it's just from the sun or from some astrophysical source. There are a bunch of neutrino experiments actually in Antarctica, and the most famous one is Ice Cube at the South Pole. It's a cubic kilometer of ice that's basically catching neutrinos that detect that interact with that cubic kilometer of ice, coming from various astrophysical sources. So, well, some of the neutrinos are noise. They come from other interactions that are not astrophysical, but that's their intent, is to capture the astrophysical source neutrinos, and that's what that detector is trying to do. There are some other ones too, but basically, this is all neutrino stuff that I just talked about for a few minutes here, and it's not dark matter. So people thought, yes, interesting, yes, yeah, neutrino stuff is interesting. It's what I worked on myself. So I can talk too much about it, but I'll try to keep it short. Pretty much, neutrinos are elusive too. And they're a type of lepton. And when they were first discovered, they're so low mass that people thought, do they even have mass? And like, what are these things? Turns out they have very low mass. There's like 3 flavors of them: electron, muon, tau neutrinos. And you get a ton of them actually, but they're still very elusive and difficult to catch. You'd have to be very intentional with the neutrino. You can't just expect to bump into them. They're introverted particles, so you have to have a very nice date set up for them to come in contact with something, hopefully a good medium of either ice, water, salt, something, and then you can try to detect them through some other things. Intricately put, what is your major or PhD? Physics. I got a degree in physics and physics and physics. All my degrees are in physics. Thank you. Thank you. So that's what the neutrino is. That's next in this book as well. Why? Because neutrinos were a good candidate or a guess for dark matter. There turns out probably not dark matter, but still a and also, of course, we talk about the neutrinos here because they're part of the cosmic inventory. So we're taking inventory of the cosmos, right? We're taking inventory of everything there is in the universe. So we've discussed photons, not too much today, yesterday, but we know that photons are a part of the universe, number 1. Number 2, baryons, the stuff that we are made of, you and me, protons, neutrons, electrons. Dark matter, this is uncomfortable, but there is something called dark matter. Has to be, because the matter density is much bigger than the baryonic matter density. So 3rd thing in the universe is dark matter. And then 4th thing is actually neutrinos, when we take inventory of the cosmic components. So the next component we need to consider is the neutrino. Unlike photons and baryons, cosmic neutrinos have... So this is where I think when the book was written, maybe they were not discovered, but we have seen neutrinos from extragalactic sources, from astrophysical sources since I think this was written. But basically neutrinos were kind of less understood even like 20 years ago. There's astroplasma, particle. Yes. Yeah, I did particle astrophysics. Astro, plasma, particle, nuclear, quantum. Yes. There's all, yeah, condensed matter, laser, molecular, optical, astrophysics, cosmology. This is cosmology. Yeah, my PhD was in the cross-section of astronomy, astrophysics, and particle physics. Some people call it particle astrophysics. It's basically astrophysics done with particles other than the traditional visible light. So like astrophysics done with gamma rays, astrophysics done with cosmic rays, or in my case, neutrinos. So I'm in that family. It's a very small, everybody knows everybody kind of family, actually. But yeah, so basically, if you did something like what I did, particle astrophysics, pretty much it's going to be like you're probably well prepared to study or try to find dark matter, because in particle astrophysics, it's very common for you to try to find something and not really get it. And then you have to put some kind of constraint on your search And what you do is put constraints on your theoretical predictions that, like, say, for example, I mentioned the WIMP, right? Like, I'm not a dark matter expert, but I imagine how it goes is the following. They say they're going to do a search for WIMPs. They look for it, they don't find it. So then, so then they probably will put a constraint on the theoretical prediction of WIMPs. How many WIMPs you should have got, like the theory that predicts WIMPs, putting a limit on that, basically saying, hey, you said we would find it, but we didn't. So here's your boundary, and things like that. But at the same time, we're talking about elusive things here, so it's also very difficult to do these experiments and to do these measurements. And not only that, it's difficult to say that you've discovered something because then you have to statistically prove that you've discovered it, and that's a whole pain and a lot of analysis and statistics, and it takes time. So they're working on it. We're working on it, and I'm sure something good will hopefully come out. While we talk about dark matter candidates, I should mention they also consider the macho, because something was called the WIMP. Then there's the macho people, massive compact halo object. That was another candidate for dark matter as well. People thinking that maybe there are just some machos out there in the galaxy, in our own galaxy, objects, compact objects that are just so dim. They have mass, but they don't emit much light somehow, and therefore they cannot be seen. So yeah, people thought that too. So there have been, in other words, this is an ongoing effort. Trying to figure out the question of dark matter is an ongoing effort, and different people have different approaches to dark matter, and depending on the subfield that you're in, you might end up working on it differently. So looking for machos, for example, compact halo object that are very dim, I suppose, that would be more of an astronomy-y type of approach. Looking for the WIMP in an accelerator might be a particle physics way of looking at dark matter. Looking for, say, WIMPs through their interaction in the ice, or I actually don't know. Actually, no, the WIMPs would not interact in the. They would not interact in the ice. I don't know. Like, basically some other thing that might happen with WIMPs, and trying to look for that in some sort of way. What do they do? I know of one experiment that's in Antarctica. I have to look this up. I'll look it up for next time, what they exactly do. But basically, if they're looking for WIMPs, say, from the galaxy somehow, then, yeah, okay, then that might be an astrophysics experiment. That's what I was trying to get at. But now I'm confused, because now I'm thinking about what that particular experiment is doing. I will look it up. I don't know if they launched yet. So, these are very more current, recent things. But then, I mentioned a few different approaches to dark matter just now. Keep in mind that those are the astrophysics, astronomy, particle physics-y ways, right? There's also a cosmology story, right? So we will actually get into cold dark matter, which is the cosmology candidate for dark matter. And exactly, the experimental side is becoming quite daunting as time progresses. Oh yeah, yeah. I actually the experiment I'm thinking of it is GAPS. Is if somebody knows, I know it's at MIT. I completely forget what their detection method is, but basically, if you're doing some kind of particle astrophysics-y experiment, trying to look for some kind of particle through its interaction or whatever, some other signature of it. Basically, you would be looking for some signature of something. I only know it in the context of neutrinos and cosmic rays, so I'll just stick to that. Stick to my lane here. But basically, for the case of neutrinos, we looked for signatures of neutrino interaction in the ice. And because we basically are saying that when we have very high energy neutrinos, they would interact with something like a quark in the ice, and there would be like Cherenkov radiation from it, and depending on the scales you're looking at and the energies you're looking at, there would be a particular signature, and we're trying to basically get radio waves to come out of these interactions from the ice in Antarctica and look for them from above. So I worked on a balloon-borne radio detector of neutrinos. So that's how and then we also actually end up being a cosmic ray detector, because you can get cosmic ray air shower signatures that happen as well in the other polarization. So details, but basically that's how, for example, particle astrophysics experiments work. I'm just mentioning all this to give you a flavor that depending on your approach, the thing you find or don't find will be different, and that will lead to it's okay to not find something, because then you can say that you didn't find it, and whatever theory predicted it, it has to be constrained. What are your thoughts on the FCC machine and its future? I don't know what is the FCC machine. Agreed. Shinobi says, thank you. I don't know what the FCC machine is. You let me know what it is. Evil green dog. So anyway, what I just mentioned was particle astrophysics experiments that I know of, which are mainly to do with neutrinos and cosmic rays of extragalactic origin. So, real quick, neutrinos are a good cosmic messenger because they don't interact with the electromagnetic field. So they don't get deflected by magnetic fields, for example, because, there could be magnetic fields in the galaxy that deflect them, but neutrinos, they just don't care. They point straight back to wherever they came from for the most part. So in terms of astrophysical messengers or cosmic messengers, we consider things like photons, neutrinos, cosmic rays. Cosmic rays are just charged particles, nothing. So basically like baryons. And generally they have charge and they interact with our, they might make something like an air shower. And the ones that are interesting would be like the ones that came from a different galaxy or something. People use them for various measurements and experiments as well. So another cosmic messenger. So pretty much I mentioned photons. So some of the things we're talking about from cosmology, right? Photons, baryons, and neutrinos. There you go. Those are the things we actually understand. And we use all of them to do astrophysics, astronomy, and particle physics experiments to learn more about the universe. But there are also things that we understand probably exist that we don't understand, which is dark matter and dark energy. Future Circular Collider, its purpose is to predict different theories in... Oh, okay. FCC, Future Circular Collider, okay. Different theories in particle physics. Yeah, I mean, I know there are a bunch of colliders. The big one is the CERN, the Large Hadron Collider. I'm not much into the collider physics, actually, so there's probably more colliders that are coming up that they're building. So in particle physics, it's really dominated by a lot of collider stuff, right? Like people colliding particles, people accelerating man-made or human-made. So actually, here's an interesting thing. So all of these things, the colliders, the Large Hadron Collider, I think Fermi Lab has something too. This thing, I don't know where it is. These colliders are to basically create an environment for particles to interact in, where they're basically humans basically make them accelerate a lot. And in those types of environments, in those human-made accelerators, we want to see what kinds of physics we might pick up on. We might theorize about a particular type of interaction, which would have a certain signature. And if we see it in that collider environment, then we can say, well, this means that we found this thing. Say, for example, the Higgs boson was discovered in 2012, right? Things like that. So they might be looking for something like dark matter in such a way where someone might theorize that, well, if you did this type of thing and if dark matter were to show up in this type of interaction, you would see this signature. So do this thing, build this collider, make this interaction happen, and then collect the data and see if you get the blip for dark matter, for example. Right? So this would be the motivation for something like that. And so that would be a particle physics approach to finding dark matter. Yes. So that would be, so that's what I'm saying. You could have a particle physics way of finding dark matter, astronomy way, astrophysics way, cosmology way, all these different approaches. So depending on which approach you want to do, you want to pick the right subfield after you get into grad school or something like that, or as a staff scientist. So so that's the particle physicsy way. I'm not sure. I'm not myself a huge fan of the particle physicsy way. Although I come from a line of particle physicists. My advisor is a particle physicist, so I was forced to learn about that. But I'm a fan of astrophysics more. So basically, I was gonna say why I even mentioned these boring colliders. I think they're a little boring, but I'm sure that they're very much motivated. I actually like natural particle accelerators. So I like, for example, an astrophysical natural particle accelerator, for example, like a black hole or a gamma ray burst. That's like much more my thing. So I have a little review on this actually on gamma ray bursts that I can cover at some point here as well. But basically, I was going to say that we are building accelerators here on Earth to study these types of particle physics so that we can understand and learn and discover new things and understand better about certain interactions and maybe find dark matter. But then the nice thing is, even though they're very far away, nature actually also gives us particle accelerators naturally. So there are certain events and environments where particles are naturally super duper accelerated. And if we can probe those, then we would also be able to study these things. But I know it's kind of hard because those events might be pretty rare. Gamma ray bursts are pretty rare and they're very far away. They happen very far away. So, but that's my little bit on that, is that speaking of colliders, they're human-made accelerators, but there are also the natural accelerators, which I like a lot. But those are all the particle-y and astrophysics-y type of things. In cosmology, we said that we have neutrinos now. There are things that are known about the neutrinos. They used all of that, and neutrinos are also fermions, so they were able to use the Fermi-Dirac distribution function to basically come up with an estimate and an equation for the neutrinos in the universe to get the cosmic inventory of neutrinos. And they found that obviously, neutrinos don't exactly oh, I see what you were saying. Energy density of one generation of massive neutrinos as compared with the density in the CMB. At high temperatures, the ratio is a fixed constant. At low temperatures, the neutrino behaves like non-relativistic matter, scaling as a to the minus 3, and so begins to dominate over the photon density, which scales as a to the minus 4. So is that what you were talking about, Shinobi? Yeah. The gamma ray burst is a beautiful, okay, good. The gamma ray burst is a beautiful, brilliant, and quite frightening topic. Very interesting. Yes. So gamma ray bursts are transient events. Depending on the part of the emission that you look at, prompt or afterglow, you get different things, photons wise, as well as other particle wise. Neutrino too is something that I was interested in looking at from gamma ray bursts. I don't think, I think now we saw gravitational waves, right? From the neutron star merger, as well as the short gamma ray burst signature. So we've actually seen some really exciting evidence of these events in a multi-messenger kind of way. Like we've seen I don't know if we saw we might have seen the neutrino from the prompt emission. I have to double check, but I know we saw the gravitational wave and the light wave simultaneously, and confirmed that neutron star mergers can give us gamma ray. That gamma ray bursts, some of them are associated with neutron star mergers, because some of them are, so gamma ray bursts, some of them are associated with hypernovae, like really big supernovae. Some of them are associated with neutron star merger, or black hole merger. And now we're, with the discovery of gravitational waves too, now we can potentially get neutrinos, photons, gravitational waves, all of this from these types of natural events, and also particle accelerators. But yeah, something in that vein of things, if we were to find dark matter, then that would be awesome. We would know what dark matter is. So far, we don't. So that's sort of in the vein of things. Now, speaking of dark energy, right? That's the fifth thing. So we talked about photons, we talked about baryons, we talked about dark matter. We have some ideas how to probe dark matter, as in how to, find dark matter. We haven't yet, but we can try. We have some candidates for dark matter. We have something. We have some of the candidates not so good, as in they thought it could be neutrinos, not really. But it seems like there might be good efforts underway to figure out what dark matter is. But what really baffled people is this fifth thing, which is dark energy. So out of the 5 things, there are 5 things in the cosmic inventory. Photons, we get it. Baryons, we get it. Neutrinos, we get it. Dark matter, we don't get it, but we are trying. Dark energy is the 5th thing, so we will talk about that now. Okay, so the other nice thing though about dark energy is that because cosmologists have these different cosmological models of the universe, it's almost like, because if you know about the other things in your inventory, it's almost like you can finagle those and see which fits your model the best and also agrees with the evidence. So this is sort of the approach here that he has talked about in figuring out how the heck they understood that dark energy is very important. Okay, so there are 2 sets of evidence pointing toward the existence of something else. Something beyond the radiation and matter itemized above. The first comes from a simple budgetary shortfall. The total energy density of the universe is very close to critical. We expect this, like 25%, 20%, yeah. Dark matter makes up around 20% of the total content of the universe. Yes. And baryonic matter is around 5%. So, yeah. So we expect this, theoretically, the total energy density of the universe is very close to critical. So we were talking about the critical energy density of the universe, and we think, according to right here, the total energy density is very close to critical. We expect this theoretically, chapter 6, and we observe it in the anisotropy pattern of the CMB. Yet, the total matter density inferred from observations is only a third critical. So this 30%, that's the total matter density. So you've got the correct ratio, evil green dog, but that's including baryonic matter. So basically, which is fine, baryonic matter plus dark matter is giving us 30% of the critical density. It accounts for 30% of the content of the universe. Suji Mama is having zoomies. The remaining 2/3. So now we're going to talk about the remaining 2/3. The remaining 2/3 of the density in the universe must be in some smooth, unclustered form dubbed dark energy. Smooth, unclustered form. The second set of evidence is more direct. Given the energy composition of the universe, one can compute a theoretical distance versus redshift diagram. This relation can then be tested observationally. So we have a bunch of redshift data, and we will read about that. Basically, they took a bunch of data with supernovae, and they looked at things that have an intrinsic same luminosity, but their apparent magnitude of the luminosity will change if the universe is expanding. So we will talk about that right now. Hi, oh gosh, hello. In 1998, two groups, Reis et al. 1998, and also Perlmutter et al. 1999, observing supernovae, stars dying, very energetic explosions, basically very bright, big, lots of luminosity giving, explosion giving things. Dark matter, yes. It doesn't interact with the electromagnetic force, making it difficult to absorb, reflect, and emit light. Very interesting. Dark matter, yes. Yes, exactly. And neutrinos also don't interact with the electromagnetic force, but they do interact with the weak force, as well as they have a low mass, so they interact with gravitation. So we thought that maybe neutrinos are dark matter, but they're not. At least we don't think that neutrinos account for most of the dark matter that we think there is. So yeah, that's dark matter. Now we're talking about dark energy. The fifth thing. We've talked about photons, baryons, which is neutrons and protons, and electrons in this discussion, neutrinos, and dark matter. All done. Those are all done now. We're talking about dark energy now. Hey, guess what? There's also this thing called dark energy. So they collected, so for dark energy, they collected data from a bunch of supernovae in 1998 and 1999. The evidence is based on the difference. So listen to this. The evidence is based on the difference between the luminosity distance in a universe dominated by dark matter and one dominated by dark energy. So we know that if the universe was mostly just matter, including dark matter, then we can basically say that the universe is dominated by dark matter because we know that it's a lot more than baryonic matter. So you can almost make two models of the universe. One is dark matter dominated and one is dark energy dominated. And then you can shift your parameters until things match the evidence. So luminosity distance is larger for objects at high redshifts in a dark energy dominated universe. So in other words, objects of a fixed intrinsic brightness will appear fainter if the universe is composed of dark energy. So if dark energy is making things expand out, then those same things which have intrinsically the same luminosity will appear fainter. More concretely, the luminosity distance can be used to find the apparent magnitude, small m, of a source with absolute magnitude, big M. Magnitudes are related to fluxes. There's some equations here. Long story short, the two groups that did the research measured the apparent magnitudes of dozens of type 1a supernovae, which are known to be standard candles. So in astronomy, there's this thing called candle. That is, they have nearly identical absolute magnitudes Although they were able to place tight constraints on dark energy using the many supernovae that they detected, we can get a feel for the measurement by simply considering two of these. So just for the discussion, we'll consider two of these supernovae. Consider then supernova 1997 AP, found at a redshift of 0.83 with apparent magnitude of small m 24-ish, and supernova 1992 P, found at a low redshift of 0.026, so much lower redshift, with apparent magnitude of around 16.08. Yeah, 16 is a lot less than 24. Since the absolute magnitudes of these are the same, the difference in apparent magnitudes is due solely to the difference in luminosity distance. So something has distanced them out more. And that's why there is a difference in apparent magnitude. The nearby luminosity distance is independent of cosmology. So, you know, stuff that's nearby hasn't expanded out yet. The nearby luminosity distance is independent of cosmology, simply equal to z over big H naught. So that's 0.026 over the H naught in this case. Therefore, the only unknown remaining in this equation we're doing with the apparent magnitudes is fixed by the observations to be around 1.16. In a flat matter-dominated universe with matter density of 1, the luminosity distance out to a redshift of 0.83 is equal to 0.95 over H naught, whereas a universe with matter density of 0.3, so if the full thing was all matter, then the matter density would be just like 1, right? We said it's 30%, so it's 0.3. So if it's 0.3, then the cosmological constant, whereas a universe with matter density 0.3 and a cosmological constant, so now we have a cosmological constant, big omega lambda, where the lambda is the dark energy, is 0.7, has a luminosity distance of 1.23. So basically we saw that this number that was 1.16, now we can consider the densities to be, we can play with the density numbers, and we see that if you take matter density to be 0.3 and cosmological constant, or the dark energy density basically, to be 0.7, then you get something like 1.23, which is similar-ish to 1.16. So the apparent magnitude of this single distant supernova then suggests that dark energy pervades the universe. So basically, in order to get the number that we got from observation for the apparent magnitude, which led to that luminosity distance thing, that same number you can only get when you consider dark energy to be a dominant content of the universe. You cannot get that with a matter-dominated universe, meaning that matter density is now 1 instead of 0.3. Yes, it definitely plays a big role in our own galaxy as well. Dark matter, yes. Dark matter is incredibly difficult due to the fact that it's practically invisible. Yes. As you're speaking, I'm looking at the charts for it. Really? Yeah. I'm on Scott Dodelson page, Modern Cosmology, page 48. Yeah. It seems to somehow hold our Milky Way together. So yeah, dark matter seems to, so depending on, again, which type of person you ask, in astronomy, people will be very interested and motivated by dark matter because it does seem to play a big role in galaxy formation. Not only, so cosmologists think that it plays a role in structure formation, large scale structure formation, in the universe. So that's the cosmological. Oh, good. Shinobi is with us on the same page. So cosmologists like not like, but they need dark matter in large scale structure formation type of things. It motivates that. But even in our own galaxy, there seems to be a big role played by dark matter, yes. But these are all still being researched. So while highly popular, so basically, yes, you're looking at this plot right here. It kind of shows you, basically they're finagling the matter density and the dark energy density or the cosmological constant to see what can you do to shift these that will then actually match the observation. And when you consider cosmological constant, so remember when Einstein worked on the equations for gravity, for the universe and wrote down the equations for gravitation, and he introduced something called cosmological constant to stabilize the universe. He called it cosmological constant, and even now some people might refer to it as that. But the thing is that we don't still call it cosmological constant, we call it dark energy. First of all, this popular name has stuck, but second of all, because cosmological constant would imply that it's constant. But that's not necessarily the case epoch to epoch of the universe. So this is where it gets really eerie. So I was like, what? Like the energy content of the universe, or the content of the universe has, or energy content, whatever you want to call it, right? The content of the universe has evolved over time. So dark energy, we need to give it some kind of density to do the math, but it also should probably be kept kind of flexible, and then you can plot it out. And yeah, you're probably now looking at the next plot here, figure 2.8 on page 50, because basically you want to see allowing for certain different types, different equations of state, basically giving you flexibility in how much dark energy as a function of the matter density. You want to see which of that fits your observation the best. So you don't want to be too rigid in your cosmological constant or dark energy density. So when they did all that, basically, what did they find? Oh yeah, they were basically saying the two free cosmological parameters in this discussion of figuring out how much dark energy or whatever there is, basically in this graph, the things that are freely moving is cosmological parameters are matter density and the cosmological constant. But the problem is, later on we will see that it cannot be the cosmological constant really. There has to be some more degree of freedom there. Something we now recognize as one possible form of dark energy, one in which the energy density is constant. Note that the theorist's dream in universe would be flat and matter dominated with the matter density of 1 is excluded with high confidence. So this matter density 1 model of the universe is now excluded with a high confidence. That's not what's going on. Indeed, even a pure open universe with matter density of 0.3 and cosmological constant of 0 is strongly disfavored by the supernova data, because we saw that the supernova, the luminosity distance was increasing, meaning that at a higher redshift, like those things were getting fainter because it's getting pushed out, like something is expanding the universe. Like it or not, while highly popular, this figure 2.7 suffers from two drawbacks. It allows for too much freedom in one sector and too little in another. Most of the region in the figure is taken up by a universe with both dark energy and non-zero curvature. That's not flat, so more like a closed. Although one or the other of these has been argued for, seldom have cosmologists suggested that the universe contains both. Thus, except for the flat line and the cosmological constant equal to 0 line, most of the region is at least aesthetically unappealing the figure allows for too much freedom. On the other hand, the only form of dark energy budgeted for is the cosmological constant. So, to open up other possibilities, we consider this another equation, this another state, the Hubble law. Yeah, where? Say more about the Hubble law. That's good. So, so anyway, now they're letting cosmological constant correspond to a small omega of -1, 0. They're letting it kind of, you know, go have these shapes basically, where in the y-axis we have equation of state omega as a function of the matter density. So now a cosmological constant corresponds to omega, small omega of -1, matter to small omega of 0, and radiation to 1/3. Yeah. With this new freedom, let's see what the supernova data imply for the equation of state of the dark energy if we fix the universe to be flat. So we're now fixing the universe to be flat. There are three possibilities: flat, open, and closed. Oh, good. I'm not too familiar with this topic. Oh, good. I'm glad it's helpful. So out of the three possibilities, let's now consider flat universe, okay? So flat means if you have two free particles, they will just stay parallel forever. Closed means that they would meet. Open means that they would keep going farther and farther apart in the universe. So if we consider a flat geometry, because remember in our discussion earlier, well, you know, before that, basically when Einstein came up with general theory of relativity and those equations, which were pretty hard to solve exactly, but lots of people, different people gave it a shot. And they even realized that depending on the, you know, energy density of the universe, you could even come up with different models for the universe: flat, open, closed, you know, and the math would work out differently for each case. So basically, you know, you can do the math all day long, you know, even if you do it wrong, well, it's fine. There's three ways to do it, right? So try each one and see which one works the best. Oh yeah. Yes. Oh yeah. So Hubble, right. The expansion is happening. Yes indeed. Yes, I love Hubble. He gave us such nice observations. Yes. So basically, when it comes to cosmology, though, since we have the tools of general relativity and Einstein's equations already, it's almost like you can always do all of the math. Don't feel shy. Just put in flat universe, put in closed, put in open, do it all, right? And then for each case, you can use that. You can also try out the different parameters of, like, sure, go ahead and do dark matter dominated universe if you thought that was, you know, good, and you can see what that does. And if it doesn't describe the evidence well, then you can finagle those numbers. And basically they found that you needed the dark energy number. So it's like another way of putting this fact, which is that we need the dark energy content in the universe. So in this figure where we have those equations of states, we see that small omega greater than around -0.5 are disfavored. A cosmological constant is consistent with the data, but it is by no means the only possibility, right? There can be other yeah, I'm sure. Yeah. So then this equation then, actually I forget exactly what this is. This was the, at one point he references conservation law of the expanding universe and says that basically we can integrate that conservation law to find the evolution of the dark energy and get an equation for that. It's kind of a little complicated, not too bad. And then we come to this next part, which is the epoch of matter radiation equality. The epoch at which the energy density in matter equals that in radiation is called matter radiation equality. So isn't that quite nice? Einstein's theory of general relativity is incomplete though at this moment until further research has been discovered. Okay, do you mean for dark energy? Yeah, I don't know. So, because we know that the universe was radiation dominated in the beginning, in the early parts of the universe, but at some point it became more matter dominated by radiation, it's just photons. There was probably a time when, yes, okay. Yeah, because we don't know what dark energy is, of course, our understanding of the universe is incomplete and there needs to be more research for sure. And it's a very important part that's incomplete as well because obviously we're doing all this math, right? And finding that dark energy is a very big part of the content of the universe. It's like 70% of the content of the universe. And so even though we had to do some finagling of the other things and we had to collect the evidence observationally to see that yes, the universe is definitely expanding, and then we fitted the energy density of dark energy with other possibilities, and we saw that the setup, what's another word, the mix of things that helped us to properly describe the observation was that you needed dark energy to be 70% and dark matter or matter density to be 30%, out of which 5% is ordinary matter, which gives us the overall picture of 5% ordinary matter, 25% dark matter, and 70% dark energy. So we had to put it all together like little puzzle pieces. Like we understood about matter density, we understood about universe's overall total density, critical density. So after putting a lot of other puzzle pieces together, and by coupling that together with the observation that gave us that those things were expanding out, like those supernovae data gave us that at high redshift there was definitely the expansion of the universe happening, also giving us a need for dark energy. So again, dark energy, it gets this name, it's a popular name that stuck. Really, it's something that we don't really understand, but whatever it is a high it's a highly dominant part of the setup of the universe right now. It's a part of the cosmic inventory, and we are still doing the research on what exactly it is. Awesome, thank you. So, but this is interesting though, that because we know that at one point the universe was radiation dominant, there had to be an epoch when it kind of became equal, matter and energy. So this has a special significance for the generation of large-scale structure and for the development of CMB anisotropy. So this is another interesting thing. They might want to look at this timeline and try to figure out what different things might have played a role in that epoch, right? So because perturbations grow at different rates in the two different eras. So later on, we will see that in the smooth universe, even though the universe is mostly smooth, there are anisotropies or inhomogeneities or perturbations around the smooth universe, which will tell us about things. And those perturbations apparently grow at different rates in these different epochs or eras, radiation dominated versus matter dominated. And so it's a useful exercise to calculate this epoch of matter radiation equality. So we do that and we find something here. we basically found the redshift of equality. So by doing this clever math and utilizing our understanding of the scale factor, we actually found the redshift at which this equality happened, which is pretty cool. Note that as the amount of matter in the universe today, that is the matter density times the Hubble constant squared, goes up, the redshift of equality also goes up. For our purposes, it will be very important that the redshift of equality is at least several times larger than the redshift when photons decouple from matter. Thus, we expect photons to decouple when the universe is already well into the matter-dominated era. Okay. So yeah, so now we come to summarize. The smooth universe can be described with the Friedmann-Robertson-Walker metric. So we got Einstein's equations, remember, back in 1917, 18, 1919, whatever, those types of timelines, and then different people solved them for different cases. And this metric, this basically, it's one example. Boom, there it is. What? Yeah, this can be, this metric implies the physical distances are related to coordinate or co-moving distances with the time dependent scale factor A of t. The time dependence of the metric is determined by Einstein's equations. So Einstein was very useful for all of this. This is all coming from Einstein. I understand that it's not complete, but general theory of relativity is pretty darn amazing in the sense that it's over 100 years old. And look at us. I mean, I feel like all of cosmology just came out of it. You know what I mean? It's just amazing. This is why how you broke down the way you explained what you were discussing. Oh, really? What did I do? I forget. But basically, this is why I took such a long time in the month of November to go over the 20th century, special theory of relativity, general theory of relativity, in a sort of consumer-friendly way, not going into too much detail, but sort of going over it, because it is so very important to understand that back in that time when we did that physics and Einstein gave us those theories and math and the ability to do the math for the universe and different people, Friedman, Robertson, Walker, even what's his face? Schwarzschild solved his equations exactly for something like the black hole, right? And we got the Schwarzschild radius. They thought black holes were crazy back then, dark star, but turns out that dark star is actually a very real thing. They're not so crazy, they're just black holes. Things like dark matter and dark energy, those are crazy, we still don't get them. But basically, back in those days, the physics that was done back in those days, in the 1910s and 20s, that's what we're reaping the benefit out of even now, and the entire field of cosmology has kind of come out of that. And the equations that have been solved, you can once you have a way to write down the equations for the universe, you can even think up different models of the universe, and you can change things. And after that, it becomes more possible, and we can do this inventory stuff that we just talked about. We can change how much dark matter there is and just see, okay, what does that work for us or not? So. But the tool that has been given to us by general theory of oh good, yes, yeah, you should come to all my lives. Yes, good, I'm glad you're liking it. Good, very much in tune with you. Very good, yeah, that's awesome. So the tools that we got from general relativity, we talked also about how he wanted to do the grand unified theory. He wanted to have a better, more general theory that would unify relativity with basically relativity and quantum mechanics. He didn't really, a lot of people didn't really like quantum mechanics, right? How bizarre it was that you needed these probabilities and uncertainties and things like that. So he also wanted to work on the grand unified theory, which did not quite pan out. But this tool we got from Einstein back in those days, this has given us this whole field of cosmology, pretty much in my mind. I mean, a lot of people have contributed, I'm sure, but this is really cool. So anyway, the time dependent of the metric, this Friedman-Robertson-Walker metric, is determined by Einstein's equations. The time component of the Einstein equations reduces to a flat universe. So pretty much we think the universe, the geometry that we currently accept for the universe is basically the flat one. Then there's some more math. And then we basically say that we just summarize. So we know that the cosmic inventory is again photons, baryons, dark matter, neutrinos, and dark energy. Thankfully, we understand three of these things, photons, baryons, and neutrinos for the most part. Thankfully, we understand that photons will follow Bose-Einstein distribution because they're bosons. Thankfully, we understand baryons also for the most part. Their distribution is kind of different, but we kind of understand them because they're just protons and neutrons. Thankfully, we also understand that neutrinos, which is the third or fourth component, depending on how you count, is a fermion. So it follows the Fermi-Dirac distribution. So we can also write down equations for that. But the neutrinos, unfortunately, are very low mass. You came here for the cats. I know, yeah, there are cats too. There are cats too. Some days I only show the cats. Some days they take a break and I show my face, and other days they're the ones who are being shown mainly, and it's just my voice. But neutrinos were great. You know, people thought maybe they can explain this dark matter thing, but they are too low mass. So inconveniently, they don't really explain dark matter. But thankfully, they're fermions. So at least we can write them down thanks to Fermi and Dirac, Fermi-Dirac distribution. So early on, this ambiguity of neutrino masses is irrelevant since the temperatures are so much larger than the masses and neutrinos behave relativistically, thank God. Thus, the uncertainty in neutrino mass does not affect Big Bang nucleosynthesis at temperatures of order 1 MeV. So something we discussed earlier is Big Bang nucleosynthesis. Actually, we didn't do that too much today, but Big Bang nucleosynthesis is another thing that we talked about. But pretty much we're saying that right after the Big Bang, things were so hot, you couldn't really make atoms and things like that. And you had temperatures of order 1 MeV and probably not even the epoch of matter radiation equality at temperatures of order 1 eV. So this is where neutrino masses might not really matter. The neutrino temperature is a factor of 4 by 11th of 1/3 smaller than photons temperature because photons are more extroverted than neutrinos. They have done more things and they were hotter. This and the difference in statistics implies that a species of massless neutrinos, they actually have a little bit of mass, has an energy density equal to around 0.23 times that of photons. So this is the summary of the neutrino math and inventory, and the mu neutrino contribution, neutrino density contribution is around 0.01 times some stuff, not too important. In addition to photons and neutrinos, the universe consists of baryons, of course, thank God, best determined by nucleosynthesis to have around a density of 0.02-ish. So 0.02, which then later on we say that it's really between 2% and 5%. And then dark matter, we got 0.3 as the density, and dark energy we got 0.7. And see, all of this is a summary because we saw that we were getting slightly different numbers depending on the measure you were taking, depending on the way you're measuring the density. For dark matter, sometimes you might get 0.25, sometimes you might get 0.2, sometimes you might get 0.3. But also, after you do your measurement way of getting the density, you can also put it in to the model and see whether it's fitting your evidence or not. And when they put in dark matter or just matter density of 1, saying that the universe's content was mainly just matter because neutrinos, who cares, are small, then and baryon density 2 is, much less than dark matter, or it's included in that matter density thing, then they didn't get the right answers, so they had to put in dark energy density, you know so then this dark energy density, it's real. We can't avoid it. We can't. Okay, first of all, we're seeing the expansion of the universe, God knows why. And on top of that, basically, this math doesn't work out without it. So a new a new form of energy with negative pressure. That's what we say. Dark energy is negative pressure, as in pressure would be like pressure, and then dark energy is like, I'm expanding. So negative pressure. There's that's my description of it. There is significantly more energy today in non-relativistic matter than in radiation. Back in the day when the universe was first forming, thank you. I'm really liking your feedback. It helps a lot. Back in the day when the universe was first starting out in its early days, it was radiation dominant. You know what? So relativistic, it was relativistic, right? So, anyways, who cares? I think we got it. I think we understand photons. I just had a thought that I hope that they did the math correctly but they would have, right? So we didn't really cover it too much today, but basically the photon math would have just been, it's all fine, because the Bose-Einstein distribution, photons in the universe, we should really understand quite well. Relativistic, obviously, but it should be fine. So sometimes you wonder if they did all the math correctly, but I think they did, because literally the 3 things that we understand, we have very good mathematics from all other parts of physics too, because there's a thing in physics called thermodynamics or thermal physics or statistical physics, depending on when you take it. And those classes will beat into you the how to do the distributions of these different things, like how to write down the equations of like photons and baryons and things like that. So it should be all fine. So anyway, nowadays, the universe is not radiation dominated. It is non-relativistic matter dominated. However, there is significantly more energy today in non-relativistic matter than in radiation in today's universe. There was significantly more in radiation in the early universe. However, since the energy density, because in the early universe, you couldn't make matter, you couldn't have good things because it was so hot and chaotic. However, since the energy density of radiation scales as a to the minus 4, while that of matter as a to the minus 3, the very early universe was radiation dominated. We know that. The epoch at which the matter density was equal to the radiation density delineates these 2 regimes, and we have a scale factor for that. So we have learned a lot by kind of understanding the evolution of the universe in short from this chapter. We will get into more details later on, but basically the universe is not this constant thing. It has evolved a lot. It is, somebody said 13.8 billion years old or something like that, 13 point whatever billion years old. We have the cosmic microwave background radiation, photons from when it was only 300,000 years old. giving us this smooth universe, which people thought was very homogeneous. Wow, how lovely, looks the same everywhere. But actually, there were these perturbations around the smooth universe, anisotropies, that people have since researched, and hopefully we will find more information about those and from those. And some of it is here in this book later on that we will discuss. And overall, we have taken a cosmic inventory. We find that in the universe, we have photons, we have baryons, we have neutrinos. We also need to have and do have dark matter. We don't know what that is. And we also need to have and do have dark energy. We also don't know what that is. Unfortunately, those are the main things in the universe, though, turns out. So it would be good if we did know what they were. In short, we don't know what 95% of the universe is. Because we only understand 5% of it, which is what you and me are made of, also known as baryonic matter. Are you a college professor, or what have you done with your PhD? Researcher, teacher, or something else? Oh, yeah. I worked in a bunch of jobs. So I had sort of like a staff scientist, or I've done analyst, researcher, staff roles. And I used to, probably the last more academic role I had was just in grad school, like teaching. I taught both physics and astronomy classes. So I did a lot of teaching in grad school because of research grants not coming in on time. Like a cosmic microwave CBM. Thoughts on Voyager 1? Like a cosmic microwave. Do you mean cosmic microwave background? CMB? Cosmic microwave background radiation? But yeah, I don't currently hold an academic role other than this YouTube Academy of YouTube. But I have taught a lot in the past, and in my sort of industry roles too, just jobs and things like that. And I guess I've given a lot of talks on various topics, so I have some practice talking. Voyager, I am not the best at knowing all the NASA missions. What is Voyager 1? Remind me again, because I forget about all the different ones. What is it? Where are they going? So I've had some jobs, but I realized in the jobs that it was utilizing only a part of my physics background. Generally speaking, most of the stuff we're talking about here, like cosmology, astrophysics, astronomy, particle physics, those are not really applied in the space probe. Yeah, space probe launched by NASA, but for what? I'm just trying to remind me, what's the mission? Like, what are they trying to find? So, in the post PhD jobs I had, probably what I utilized the most from my physics background was the device and experimentation and measurement work that I did. Oh, okay. Oh, that's what I thought. Like, is it gonna go towards like Pluto and stuff, or what? Outer solar system? Okay, good. Cool. Great. Sure. So, ooh, nice. An interstellar system. Oh, good. Been in space since 1977. Okay. Perfect. So, I did radio astronomy, right? Basically, another name of what I did was, I told you about particle astrophysics, but I also worked on, what time is it? 3:20. I also worked on, hi David, Manuel David, hi Shinobi, hi Evil Green Dog. 3:17 in the morning. Good. So I worked on particle astrophysics. In the real world jobs, I don't think anybody really cared about astrophysics or particle physics, but they did care about all the detection methods that we used to catch these neutrinos and things like that. So since I did like RF work, radio frequency, radio astronomy detection, and instrumentation type of work, a lot of that carried over to my jobs that I had, various jobs I did, sort of in researchy or analysis-y type of roles. So it was fun and technical. So technical type of positions were all possible, but it was not very pure science-y or pure science researchy, these jobs. So I found that to keep up with my interests in pure physics or pure science and astrophysics or cosmology, if I wanted to study these, I'd kind of have to do it on my own. So that's what I'm doing now. Because I'm really interested in dark matter, dark energy, obviously, right? Because who wouldn't be? Right now, those are the top open questions: dark matter, what is it, and dark energy. I love science. Yay! You're on the right channel. We love science here. We love physics. We have had a lot of very interesting discussions. So people like you, who are participating a lot and in giving your own inputs too, it's very highly appreciated. I really love when people join and they say a lot of their own comments and inputs, because feel free to share anything you want from your own science and physics experiences, or whatever you're working on, because that makes for a very engaging discussion. Hi, Peter. Peter Burns says, hey, hello. So I just subscribed. Thank you, Peter. Thank you, everybody. Please do subscribe. Really appreciate it. But yeah, basically, it helps a lot when people engage and discuss. And I've learned a lot too. People talk about their own work in double E and things like that too. So it's been lovely, and you'd be surprised how many people are interested in these things. Like, people make friends on these live streams of mine, and they all like know each other after a while. So people really love these topics. And there's been a lot of very engaging discussions on these live chats that I then, also learned about things as well. So yeah, thank you for reminding me what a Voyager 1 is about. Space probe, of course, interstellar. So it's going out to the outer solar system. Do you really think the universe? Yes, because we have evidence. So I don't think that the universe is expanding in the sense that we know that the universe is expanding. I'm most definitely subscribed now. Oh, thank you. Thank you. Yeah, please make sure you're subscribed, because sometimes people hit the button and they're still not subscribed and they don't get notified when I go live. And I go live on most days and we talk about this type of stuff: cosmology, astro, physics, particle, quantum. We did a ton of quantum discussions, and they were very, very engaging. And we talked about how when quantum mechanics was developing back in the 1900s, how much drama there was around quantum mechanics. So like, we also bring in sort of the historical perspective of the development of physics, like the history of science view, basically. Thank you so much. Hi, basket of minks. Thank you. So it's almost like, it's interesting to understand about the history and sort of like political. We even talked about the wars. If you go back, after the live, if you want to check out on my channel, the live tab basically has all the old live streams, videos uploaded. We talked about so much drama back in the World War times and how that affected science. Of course, we got the atomic bomb and things like that. here's the book we were just now referencing. I'll just show it here. But basically, we've really covered a lot about the 20th century physics stuff. And it's been helpful because now when we talk about the current, more recent topics, we almost always have to reference back to what we had just talked about, because that lays the foundation for everything we're doing now. So it's almost like I'm studying here, with you guys as well. And it really helps to get this back and forth. And I found that for me to keep up to date, it's kind of like a study group, these live streams. I found that there's really no other way to do this other than on my own and with you guys here on the lives, because most jobs don't really let you. The brilliance of Voyager 1 is it's just sending us signals we can't quite interpret that takes 22 hours at the speed of light to receive messages from it. Oh, good. It's just sending us signals we can't quite interpret that takes. I don't really dive into politics too much, even though I understand it completely. I just choose not to for personal reasons. Oh, yeah. I don't talk about current politics. I only meant history. So we only talked about, I meant not politics. I meant within physics, basically there were these two camps in the 1900s. There was a more classical camp, Einstein, relativity, people wanting to come up with the grand unification theory. And then there was the quantum camp, Niels Bohr, and there was even a famous debate between Einstein and Niels Bohr. Amazing stuff. So there was politics even within physics. Even now, there might be, just be aware, especially if you're going to be a physicist yourself, that nothing is without bias. And there might be little political things going on between these different camps within physics. But it's strange. Schrodinger's cats? What's your thoughts on... Oh, what's your thoughts on Schrodinger? You mean Schrodinger, right? Is his first name Erwin? Here's the book. I'm okay with quantum. So my thing is, I'm with Niels Bohr on quantum. My thing is, if something is super confusing about quantum mechanics, but it does a good job of explaining physics of the very small, as in it does a good job of explaining what's happening at the particle level, then I don't care. So cats are not quantum, right? Cats are classical for me. So thank God, cats are a classical thing. So for me, I don't dwell on Schrodinger's cats because I'm good. See, I feel like a lot of people liked to poke holes at quantum mechanics, and that's okay. Everything in physics goes through the poking holes phase endlessly, right? It's okay. That's the nature of research, and it makes things stronger as well. But for me, I just want to learn and solve the problems that are actually out there to solve. Like the cat thing is not a big deal to me. Like if the cat thing is controversial in quantum, well, for me, cats are not quantum. So as long as it describes an electron well, I'm happy with it. You're very smart. I think I'll listen in for now. Okay. Teaching me some more, please. Yes, of course. You should come to all my live streams. You should come tomorrow, Wednesday, Thursday, Friday, Saturday. We will go live every day. Thank you, everybody. So anyway, I loved all the drama that unfolded in the 1900s because of quantum. Because just imagine, back then, quantum was new, right? They only understood classical mechanics, electromagnetism, and then relativity. And even relativity was very controversial in the sense of like people didn't really get it. I mean, Einstein got the Nobel Prize for photoelectric effect, not relativity. I think because people were too cowardly and they didn't want to give him credit for something that they didn't fully understand well yet, because they weren't probably as smart. Thankfully, they did give him the Nobel Prize for something, and he godfathered the old quantum mechanics because, yeah, because he came up with the quantum nature of light. So he also did quantum mechanics, but then quantum mechanics became much more bizarre when they started to really do quantum mechanics and describe, something like the hydrogen atom, and find that there's a nucleus, and then there's, the electron, and writing down the wave equation for the electron, the, Schrodinger, but then actually realizing Max Born realized that the Schrodinger wave equation for the electron was not for the electron, but actually to find the probability of finding the electron, not the electron. So, and then it was fine, but they didn't like that. They didn't like that things were now probabilistic when things had always historically been deterministic. Things were, even NASA, right? Like someone mentioned about Voyager 1. Basically, even now, we do classical mechanics so much. Like we launch spacecraft still using Newton's classical mechanics. When we know where that Voyager thing is now, or 22 years ago, like it's deterministic. We will know where it will be. We can predict the future of it, right? So, because at the classical scales, in the classical realms, when we know the position of like the moon or this Voyager 1, which is kind of like a moon, but not really, because it's going to go farther. But like when we know the position of that thing, because physicists are control freaks, right? They want to know at a basic level, we physicists want to know what is the position of a thing as a function of time? What is the position of Voyager 1 as a function of time, right? That's what they want to know. And that's what they historically always were able to get with something like classical mechanics, Newtonian mechanics, all the laws of physics and things like that. But then when quantum mechanics came and gave us probabilities, because now it was about the mechanics of an electron level, people were very upset. So yeah, we discussed that at length in our previous live streams. Intellectual conversations, I very much appreciate. A lot of takeaways. Yes, thank you. I love the behind the scenes squabbles of historical figures. Yes, oh my gosh. We did that a lot. I might do it again just because we enjoyed it so much. I too myself find that quite intriguing as well. Yeah. So there were a lot of drama in the 20th century because of the quantum mechanics progresses. But at the same time, even with all that drama, quantum mechanics basically was still a thing. It was basically still a thing because of its experimental successes. And guess what? Now we have particle physics coming out of it and quantum field theory coming out of it. And now we have entire families of particles. And now we have funding to make more and more colliders. Guess what? That is a win of the quantum mechanics people back then who were fighting for the development of quantum mechanics. So I'm very proud of the Niels Bohr and company people, because they won. Quantum mechanics is still alive. It's the more dominating field almost of physics, because particle physics is so big now. And then, unfortunately, for the people like string theorists, it's become a much smaller minority. Tell me if there's any string theorists in the chat, by the way, because I'd love to meet you, man and woman and anything else, because all the they, thems, she's, hers, everybody, because honestly, string theorists are rare. I don't meet too many string theory people, but the grand unification theory big candidate was superstring theory, right? So it's like superstring theory. What's so nice about super string theory? I don't know too much about Edward Witten. Do you believe there is life besides us? I believe that we have found particle physics is so big now. Yes, it's so big now. It's so mainstream. It's so mainstream. It didn't used to be. Wait, Shinobi, are you doing string theory? Come out. Come out of the closet right now. Are you doing string theory? You can tell us. It's fine. We won't we won't hate on you, I promise. I'll just say something positive about string theorists right now. They are the best at general theory of relativity. So, quiz. We will quiz you next time. Why you ask me that? I don't know, you're making those emojis. I'm getting a string theory vibe from you, man. You can say it. It's okay. I wish that more people would do superstring theory. I feel bad for the field because their theory cannot be tested. I feel like they've taken a hit. They've taken a hit because all these extra dimensions that we don't live in, unfortunately, maybe we do, maybe we just haven't seen it yet. All these other dimensions that we don't seem to experience are so hard to test that this field has really diminished. But I feel bad. I feel bad. I feel like there needs to be more that's done on grand unification theory, even if it's just, string theory. And there's no just there, but I just mean we should do more. Oh! It sounded familiar. That name sounded familiar. Supposedly the greatest theoretical physicist alive and great contributor of string theory. See? String theory? I feel bad. I feel bad that the field is so small. But guess what? That guy and, well, I'll just speak for myself. The person who taught me general theory of relativity in grad school is a string theorist. He's lovely at general theory of relativity. So GR is kind of hard, right? The math is kind of difficult, and all the notations and things you have to learn and be comfortable with is kind of difficult, or not really as mainstream like taught. So, but what I found was if you do string theory, of course you have to be comfortable with that. So those people really understand GR. So I love that about them. That is, to me, the biggest usefulness of the string theorists. It's okay. The community will rise again, hopefully. Good. I have full faith. I think there needs to be balance. We can't all be doing particle. But yeah, all the extra dimension is quite strange. We can't all be particle physicists. I fully agree that particle people are too much now. There's too many of us, of them, of whoever identifies as a particle person. So if somebody wants to be a string theorist, no hate, no judgment. Do GR, teach us GR, teach the whole world GR. We all need to be better at GR. And tell us something about dark energy too. That would be amazing. Because, somewhere we need more paradigm shifting physics. I feel like now, basically, I talked about this too. Basically, ever since all of the big, amazing discoveries of the 20th century, which mostly had to do with relativity, meaning special theory of relativity, general theory of relativity, photoelectric effect, all of these were done by Einstein and others on some of the other things I'll mention, quantum mechanics. Those were the big things, right? These were all the paradigm shifting, earth shattering things that we came up with. And after that, I feel like the focus in the 21st century has really been on measurement, experimentation, observation to, I knew it. Don't hide. It's okay. Nothing is wrong with string theory except for lack of funding. It's totally fine. It's totally so um so so I think the big thing that we do nowadays is get better and better at collecting data, at making observations, collecting more and more evidence of all these things that we are talking about and of all the things that we talked about in the 20th century. A lot of the things that Einstein predicted are now getting confirmed 100 years later, or for the 100 years that have followed since his work, right? So now we need Shinobi and company to do something new again. Because I feel like a lot of our energies and efforts these days are dedicated towards experimentation, which is all fine. It's amazing. Instrumentation, being able to observe, being able to collect evidence of all this and be able to see, as far as we can see now in the universe, all the data that we can collect and everything that we have to analyze as a result of that. All of that, all of that is all great, but that's basically mainly what we have achieved in this time, in this century, in the current times, right? We haven't really done too much paradigm shifting type of stuff, other than the thing we just discussed, where we now know that 95% of the universe is something we don't know, as in it's dark matter and dark energy, 25 and 70. That is paradigm shifting in the sense of like, wow, oh wow, like it's but it's still sort of more of a confirmation of something, because the cosmological constant is 100 years old, right? So dark energy is not a new concept. It's over 100 years old at this point. you know so I don't consider dark energy to be it's a current topic, as in we still haven't solved it, but as a theory, as a thing, it's not new. It's actually over 100 years old. And dark matter, okay, we discovered it more recently, but even by recent I mean it's still been decades, and we still don't know what it is. So what I'm trying to say is we haven't really done anything too new where our entire understanding of nature has kind of changed in the realms of these topics: astrophysics, astronomy, particle. Like, okay, we've done a lot of things, especially in instrumentation, where we can observe really well now, and that's where the main progress has been. So now I feel like we do need more of that earth-shattering, paradigm-shifting type of physics work that I'm relying completely on Shinobi for, and others. Shinobi and company. Give us your superstring theory, man. It's fine. Tell us. How many dimensions do we need? What's wrong with string theory, though? I'm just asking for a friend. Nothing! Nothing is wrong with it. Other than it cannot be tested and usually doesn't get funding. But nothing else is wrong with it. Absolutely fantastic. It's not me, it's a friend. What about the eternal dimension heaven? Oh, I don't know. She put me on the spot. I'm just a regular Joe who does string theory. Any thoughts on what's in the depths of our oceans? Oh, I have no idea. The ocean is too complicated for me. I just believe in the universe. No. Yeah, so I'm a typical physicist who loves to be ignorant about the ocean. about the earth, kind of. I mean, yeah, I don't know too much about the world. Um, didn't have time. Too busy. So, so that's a great point, though. There are people who really understand the ocean really well. It's funny, isn't it, that when you talk about the universe, it's almost simpler. We talked about the universe and cosmic inventory, and there were only 5 things in it. Now, granted, 2 of those things we don't really get, as in we don't really understand, but 3 of them we understood. And it's almost like we can do the math of these 5 different things, and we can come up with equations, and we can write down the description of the universe, but at the same time we don't know 2 of the things that are the more dominant things, so it's kind of bad, but it's kind of good because it's like we are getting somewhere. But with the ocean, I don't know what's in the ocean other than in Boston, which is where I am. There are whales. There are these humpback whales in the ocean. I only know that because I observed them on a tour, on a whale tour. But I'm really bad at the ocean. You know why? Because the ocean is the water. You know, the type of physics I did was radio astronomy, right? And that is really bad in the ocean. So I'm not good at the ocean at all. Yeah, yeah, yeah. You got it. I'll just listen to you. Yes. Yeah. Tell us something about supersymmetry and string theory right now, Shinobi. Come on. Give us you're a young bright mind. I'm gonna charge my phone. You are a young bright mind. In cosmology, everybody is young because you're probably younger than the universe. So, tell us something about superstring theory. Share your knowledge. Right now, tell us. We probably, yeah. I believe in quantum mechanics, so everything is a probably. I don't mind the probabilistic nature of quantum mechanics. OMG, why? Why not? Educate us on superstring theory. Come on. So, I remember there were those people. Wait, was it Friedman? Was it the same people who solved the equations for extra dimensions, and Einstein was really happy, and then superstring or string theory kind of came out of that? It was the same people, right? Where's my hair tie? Oh, here it is. It was the same people, right? Oh, you're not? Teach us your splendid shinobi ways. I'm not a string theory guy. So then what are you? Tell us. I don't know why she pinned me as one. I just got that vibe. I mean, who reads Cosmology at 3 a.m? You have this book. Oh yeah, 11 Dimensions, yes. Too late, you've been nominated. Yes, I've nominated you. Yeah, 11 Dimensions. Who were the guys again for that? Is it... Yeah, you've been nominated. I know a lot about a lot. Okay. Well, tell us. You can't just keep us hanging. Tell us something about string theory, because that's one thing I haven't said a lot about. So
I just am looking at the... I love Shoreshield. He died too young. But I love that he did black holes. Aww. Oh yeah, Kaluza Klein. That's right. It's not Friedman. We just talked about Friedman, Robert, Sen, and Walker. But look at this. Okay. All right. Since Shinobi is not going to tell us, string theory is okay, but I'm not really into it all that much. Okay, so what are you into? And since Shinobi is hiding, we will read about it from here. So Kaluza Klein universe. I want to talk about that. Wait a minute. I don't care about... You know what we should do? Shinobi is not coming out. You know, I pretended too. There was a time when I was a closet astronomer and I took condensed matter and pretended to like graphene and cried every time I looked at the night sky. I was in the closet of astrophysics. Don't be in the closet of string theory. You can come out. Where the frick is this thing I was looking at? I was in the closet for a year. Condensed matter physics. I thought I'll make myself useful in the world and do something that's applied more. Did it stick? Not really. I knew it. Fact is crazier than fiction. Ooh. Come on. Kaluza Klein. Maybe it's just this. Okay, whatever. M theory may also explain some of the puzzles that surround the old Kaluza-Klein universe. Recall that one serious objection to the Kaluza-Klein universe, I believe Kaluza-Klein, these two people solved his equations for how many dimensions? Was it 11? Is that the 11? This is why I needed you to talk about string theory. Recall that one serious objection to the Kaluza-Klein universe was that these higher dimensions could not be seen in the laboratory. See, and in fact, must be much smaller than an atom. So these higher dimensions, which we could not test, they were supposed to be much smaller than an atom. Otherwise, atoms would float into these higher dimensions. So the nice thing about this that I liked about the Kaluza-Klein universe is that at least these higher dimensions were so small that we don't really experience them, right? Because if they were, you know, bigger than the atom, then the atom could go into them or something, I don't know. But M theory gives us a possible solution to this by assuming that our universe itself is a membrane floating in an infinite 11-dimensional hyperspace. Yes, 11. Somebody said 11. Thus, subatomic particles and atoms would be confined to our membrane, that is our universe. But gravity being a distortion of, that's what this was. This is what upset me. I remember. But gravity being a distortion of hyperspace can flow freely between universes.
This hypothesis, as strange as it may seem, can be tested. Ever since Isaac Newton, physicists have known that gravity decreases as the inverse square of the, we know. In four spatial dimensions, gravity should decrease as the inverse cube of the distance. Thus, by measuring tiny deviations from a perfect inverse square law, one may detect the presence of another universe. Recently, it was conjectured that if there is a parallel universe only a millimeter away from our universe, it might be compatible with Newtonian gravity and also might be detectable with the LHC. So this is also probably something that they're trying to do with the collider stuff. They want to detect another whole universe. Why not? All casual like. This in turn has created a certain amount of excitement among physicists, realizing that one aspect of superstring theory might be testable. Wow! Soon, either by looking for sparticles or by looking for parallel universes a millimeter from ours. Wow. My friends used to call me a nerd. Who? You? Okay. And so what? I didn't care. It's cool to be smart. Yeah. I don't have any friends now. They all turned to be fake. Well, we're friends. We will be your friends now. We all study cosmology. Or the universe. It's unfortunate. This is what upset me at an earlier life. Because it got me thinking about dark matter, and the author here, Michio Kaku, says the same thing. These parallel universes might provide yet another explanation for dark matter. So this could be a dark matter candidate, basically, as well. If there is a parallel universe nearby, so this millimeter thing, I think, is just a theory, like a suggestion. I guess one could say that let's try it out, and then if we don't see it, then it puts a limit on, well, there's not a parallel universe a millimeter away type of thing. So basically, if there is a parallel universe nearby, we will not be able to see it or feel it, since matter is confined to our membrane universe, but we would be able to feel its gravity, which can travel between universes. To us, this would appear as if invisible space had some form of gravity, much like dark matter. In fact, some superstring theorists have speculated that perhaps dark matter can be explained as the gravity produced by a nearby parallel universe. So I really need you guys to do superstring theory and see if this is right or not. Or at least try to find this parallel universe. I don't know what to say. If we confirm that dark matter is because of a parallel universe, that would be something. That would be. Then I would say yes, in the 21st century, we have done something worthwhile. We have truly come to a new understanding of something. Because other things that we've done, although amazing, are sort of the results of the last century. In this century, what have we done, you know? Have we even found a parallel universe? Have we even confirmed about dark matter? So that's what we need. But the real problem of proving the correctness of superstring theory is not experiment. We don't have to build. Oh yeah, then he goes on to say that superstring theory is... Yes, hi Isabella.
OMG kitties where? Here's one. These kitty cats. Classical kitty cats. Yeah, that would be amazing information to discover. Yes. See, that's where things would get real. I feel like we're doing a lot and we're trying a lot in preparation to collect a bunch of data. Yeah, here she is. To collect a bunch of data. But once we start to not only confirm what was kind of given to us already in the older work, but also when we start to confirm these things about basically solving dark matter and dark energy would be really great. Just that. Do that. Yes. Okay, so I think I have a little bit more charge now. You can see. Hi, Bacha. Here's Suji. Hi, Suji. Here's Baji. Yeah. You're awesome. Keep doing it. Thank you. The kitty is so cute from behind. Yes. Thank you. Touch wood. Thank you, God. Thank you, universe. It's a brilliant strategy. She lures us in with cats, and then we learn sciencey things. I know. I used to talk about just science years ago, and nobody cared. So then now I lure you guys in with cats. I've been doing content for a while now, guys, and it's only worked when cats are involved. The internet, the internet really likes cats, and I'm a cat mother, so I passionately like cats. Babu, Suji buble. Suji wants snack time. She's like, I've studied so much. I know you did. Usually takes a few live streams for people to catch on that this is a cat come physics luring. But you guys are really smart. Yeah, no, you guys have been an excellent audience today. You guys have been so engaged and engaging and participating and talking about all the different topics. Thank you. Good strategy, well played. Thank you. Yes, bite of both. Yes, there's a lot of cat videos and also these physics type things that we do. But yeah, so anyway, if anybody wants to talk about string theory, feel free, because I feel like we're at that point now where we are ready for more of the sort of these like, we're ready for more progress in the field, in our understanding of things beyond what we know so far. I learned stuff. Thank you. We appreciate you for sharing. Thank you. I'm into Japanese culture, historical, martial arts, etc. Wow. I don't know much about that. I was born in India, but now I'm in the US. But yeah. Suji. Suji, say bye to all your audiences. Hi. Oh, look at Kyoto Ka. He's so fun. Who is that? Well, how many overlap universes do you think there may be? Yeah. Ace Wolf Peach. Hi. Thank you for coming back to the live. I don't know. I don't know how many
I don't know how many universes we got, man. Hello. Hello, Ace Wolf Peach. String theory is more mathematical than dealing with physics, pure mathematics to be exact. Yeah. Yeah, so string theory is very mathematical, but those people really, really understand and can do the math of general relativity. So they're very good people. Oh, thanks. They're very good people for that. So, that's always great. Um, oh yeah, Christmas colors. Look at that, red and green. Um, but it is very mathematical. So I, for one, did not really get into string theory. You just look like trouble. Yeah, I am. I'm like, my friends call me a toddler. I walk away. Uh, preoccupied. I went on a trip recently and they said that I kept walking away, like being somewhere. And I was like, well, the probability of finding me. Oh my gosh. Maybe. So, anyways, yeah. So, I wish that we will. Ooh, can you guys like the live? That would be amazing. Like the live, and also if you're interested, please do. Actually, no. Even if you're not interested, please do go to my channel and go under the live tab and catch up on. If you're new to the channel, catch up on our live streams in the past. You'll see, especially in November, we covered some really awesome topics. We covered all of the 20th century stuff and Einstein's work and everything. So those were really good topics as well. If you're liking this type of content, you might enjoy that. Thank you, Shinobi. Thank you. Thank you, Peter. Philadelphia experiment. What is that? Tell us. Tell us what the Philadelphia experiment is. Oh, Nikola Tesla, I love him. Poor guy. Really? Wait a minute. You remind me of a YouTube I used to watch. I forget her name. Ah, well, now I'm the YouTube you're gonna watch. I need your support. Oh, thank you. Illy something. Okay. They teleported. They teleported a ship from Virginia. Oh yeah, weren't you from Ace Wolf Peach? Aren't you like from Virginia? Is that what it is? Lily Singh? Lily Singh? That's the comedian. Oh. Oh, she's really good. She's a comedian. Lily Singh? Oh, wait. Okay, you're from Kentucky. Oh, that's right. Okay. Yeah, I have somebody from Virginia. Wait, are you Ace Wolf Peach? Were you the one who talked about the court cases? Yes? I remember something with that.
Lily Singh? Maybe. Okay. Graphene. Yes. Okay. Well, she looks kind of different. She does not look like me. Thank you. But yeah, no, she's really funny. She's really famous, so thank you. She's like a comedian. She's a comedian and actress. She's really funny. Like, she's awesome. Anyway, so, thank you guys. She's a comedian now. Yeah. If I'm a comedian, I don't mean to be. I'm just funny. Fame is overrated. Yeah, I know, right? I kind of like my space right now in the sense of I don't want it to be too crazy, but I would like to have a bit more of a, I don't know, bigger YouTube presence. But yeah. Is MySpace still up? I don't know. I don't have a MySpace. I didn't get into the internet stuff until 2008. I think I entered the internet in 2008. And I mainly just did Gmail. And that's what I did. That's what I used to apply to colleges. I didn't really do social media or anything like that. I retired boxing in 2006. Oh, like boxing? Like boxer? Like boxing? I haven't been on MySpace since the late 2000. Oh, wow. So you do boxing professionally? Oh, holy crap. Oh, wow. That's great. Actually, I get a lot of people on this live who are sort of like, they like this science and physics stuff, but they also do something very different, like boxing. In fact, I mentioned this before. I have some kids who joined the live who immediately talk about who they punched. MySpace is still working. I don't use it. I also studied martial arts for more than over 40 years. Wow. Wow, Shinobi. Goodness. Awesome. But yeah, the boxing and the punching seems to be a theme here as well. For some reason, that's true. Yes, I have people here who have a lot of experience with punching. I know boxing is more than that, but yeah, that's all my YouTube channel is about. Oh, wow, martial arts? That's awesome. Wow. Look at Baji. Baji. Baji's sleepy. Sleepy time, Baji. So, guys, will you join us in the live tomorrow? That would be amazing. Let me... Hi, Sachi Mama. Let me let you look. Oh, hi. Hi. Ocean waves. Boxing is fancy punching. I told people the other day about this topic as well. Thank you. Yes, please spread the word. I need your help with spreading the word. Sure, you take care. Good night. Y'all, thank you. Good night. How old are you? I am 4 billion years old. I told them about your channel and the fact the all science needs. All science nerds are kind of violent, lol. No, seriously though, you guys, y'all are kind of violent. I mean, that's fine, I'm sure for good reason. But, as in, I don't know, but no judgment. But some of the kids, especially who join these lives, immediately talk about punching somebody. And, Shinobi, yeah, you're peaceful, but you also know everything about martial arts. And so you like to punch people more gracefully and with discipline. Amazing. But thank you so much for telling people about my channel. Thank you. Really appreciate it. We will see you hopefully every live. Is that whey protein? It is. It is. I used the whey protein container to charge my phone and show you guys these things. I know I grew up on Japanese culture. Nice. Precision punching. But yeah, this is my whey protein. For all the iron pumping that I'm gonna do with my here's my weights. I do the gym. I bench press. I'm so proud of myself. Hi, Suji. It is whey protein. It's old because I'm not really very good at taking all the whey protein that I should be taking. So anyway, but I wanted to show you the books we referenced today, Modern Cosmology and Einstein's Cosmos. But yeah, nothing wrong with that. I should be taking more whey protein probably. Nothing wrong with that. Mine is on top of the cabinet. Yeah, I just keep mine on the counter. And I'm glad you noticed because this will remind me to take some whey protein tomorrow with my milk before I go to the gym so I can carry kitty cats. And hi, Suji. Hi. Hi, Suji. Oh, Suji Mama. Here you go. Suji Mama wanted a snack. There. We don't need that light. You have to do it by body measurement on how much you weigh for it to be effective. Okay, well, I think I weigh something like 100 and between 145 or 150, 153, something. I can't remember. It's something in that range. It's definitely over 140, I think. So how much should I be intaking? I just put a spoonful or so in my milk. I just drink 4 scoops a day and a half gallon of milk with it. Oh wow, I don't really take that much. I only drink it when I remember to. So I don't do it every day. I guess I'm counting on my other proteins intakes. 120. I just drink 4 scoops a day and a half gallon of milk with it. Half a gallon? What? That's a lot. You're in a good spot. 120. If I were about like 2 scoops. 2 scoops and a quart a day. Okay. Okay. See, I learned so much from you guys. Everybody says their things here. All the measurements of whey protein. Chachi mama, are we gonna go? Pre-workout? Okay. Cool beans. So pre-workout, take that. Okay. That makes sense. That makes sense. Don't forget. Have Nephilim. Okay. Yeah. I also swim after my weights. So like what my workout routine is the following. So I do some weights, like free weights, a little bit of like bench press, squats, just almost like a warm up. Some like, what's the thing called? Lat pull down, that thing maybe. Or like, when you put the weights up, shoulder press, I guess. Yeah. Some shit like that. I do some stuff like that. And then this is all like, I do all this, right? And then I go swim for as long as I want. And then I do like sauna. And then I, shower, get ready, come back. So that's my whole thing. Teapot? Yeah. No, I made the tea already. As in my teapot is right here. I did that already. And at this point, it's actually kind of cold. So I'm just going to drink it like water. Are you starting teapot? No. Good. Sounds like you're on the right track. Thank you. Yeah, I enjoy it. I really like the swimming part. So it's like my reward after the weights. And the secret is that sometimes I don't really do the weights. I just do the swimming. If I'm having a bad day, I skip the weights. Because sometimes, like, my weights are not even there. Like, all the guys, it's all mainly guys at the weights, right? They take all the weights and they put it everywhere. And, like, well, I try to find it. It's not an excuse. I try to find my weights, 15s and 20s and 25s. I try to find my weights, but they don't have enough of those weights. Military press, shoulder press. Yes. Yeah, I like doing shoulder press and bench press. I think my favorite are those. Ugh, I hate squats, but I still do them. Yeah. I do some of this and I do like stretching and things like that and just kind of get into a good shape of, shape as in like I get into I'm like moving and, out of breath now. And then I go swim. And it's like really nice. I like it. Swimming will let you know what muscles you don't work and where they are. Oh, yeah. Oh, yeah, you're right. Actually, when I swim, I use my arms a lot, and then sometimes I do the thing where you only do legs and you use the board, and then yeah, I really feel it in my legs. So I probably don't do legs very much. But I wear out my arms during swimming because I don't swim very like efficiently. I'm trying to go for the workout, right? But I kind of like feeling it in my arms. But yeah, it could be that my legs. Actually, yeah. Yeah, I guess I'm not doing anything specific for my legs. Huh. Other than walking and swimming. Oh, and climbing stairs. Lots and lots of stairs in the Boston area. Swimming will let you know what muscles you don't work. That's interesting. All right, so I'm gonna do $500 can let you know how weak you are as well. Oh yeah. So I go to LA Fitness and I don't really know what is the length of that? I know the length of our galaxy, but I don't really know the length of the swimming pool where I swim. And that right there, ladies and gentlemen, tells you everything about me. Okay, I'm gonna go shower actually. Y'all can hang out. Thank you for chatting. I gotta take a quick shower. You guys can hang out if you want. Thank you for being here. Thank you, thank you. I'll come back in a sec. Up. I know it's cold. I don't know if I should shower. Maybe I'll skip. No, I'll shower. Actually, I forgot something. Oh, so I have to do that like 10 times? Actually, I do it a lot of times. I usually do a lot of laps. But not like constantly. Because I get out of breath. Like I need to stop a little bit. But I do a lot of laps. I probably do... Oh, maybe I should count my laps. I probably easily do 10 times back and forth. As in like 20, you know what I mean? So, hi, Suji Mama is having zoomies. I just had thought about your channel earlier today. Good. Side stroke. What is that? I just do the, you know what I mean? That freestyle stroke thing. Like I just, the arms. swim side stroke and get a rhythm. I think I do that. I don't know what side means, side stroke. I just do my, like, you know, the thing where your arms are going and you, like you're on your belly in the water. I just do that. And yeah, the, you know, like this, like arms. I can't describe it. I think what I do is that. Maybe it's called freestyle. Not really sure. Oh my god. Side kick? Oh, that's a lot. Hi, Suji Mama. Front crawl. Oh, wow. Oh, look at Suji. She's having so many zoomies. Oh yeah, that's right. You can't see me. Here, like where I go like this and this. Like in front of me, arms. I prefer a basket of chinch. Wait, what? Hi, Suchi. Little baby. I had to take some Benadryl. Azzy. Front crawl. Basket of chinchillas. What does that mean? What is a chinchilla? Shuchi, shall we go up to bed? Okay. Air. Yes. Good. Oh, it's gonna be so rainy in Boston. It's gonna be so rainy. Good, water, good. Off, and off. Off and off. Off and off. And off. Oh. Guinea pig. Okay. They're those super soft rodents. Oh my god. Wow. Here you go, Fuji. Alright guys, thank you so much for joining. Y'all can hang out. Maybe I'll go to sleep with the live on. Is Mink Not a polecat. Oh, that was you, basket of minks. They're those super. Okay, got it. Everybody, if I fall asleep, I'm still here. Here you go. Appreciate everybody, everybody, oh. Black Street, no, not Black Street, Back Street, boys, and then what? Alive, everybody, oh. Back Street, back. I can't remember the words, but something like that. Off and off and off. Are the doors closed and locked? Yes, good. Closed, locked and locked. Good. Closed, locked, and locked. Very good. Okay, we've done the checks. Everybody in Back Street, back. All right. Dun, dun, dun. Dun, 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 dun. Yawning is contagious, yeah. How are you, friend? Now Seth. Today what for lunch? Oh yeah, I ate Chinese food today. Like an eggplant dish. Oh. I didn't realize I was promoting it. Hi, Baji. Thank you. Just because you're in Boston doesn't mean you have to promote. What? I did not mean to. Are they Butt Street? Superfood, yes. It was eggplant. I ate that. Vegetarian. Today I've been good. It just came to me. Are the Backstreet Boys from Boston? I actually don't even know. Why? I didn't do anything with Backstreet. Oh gosh, is that what that means? Oh my god! I thought that meant like a street somewhere. Like a road. I did not. This is beyond my imagination. Goodness gracious me. I know not what you speak of. I thought the Backstreet Boys was about a road. I don't know. Anything more than that. Goodness gracious me. I thought that's the name of the band. I am not from this country. That's all I'll say. I always played my foreign card as needed. Here it is. Here it is. Foreign card. I don't know. It's whatever the Americans taught me. They told me it's a road. Oh, okay. Oh, okay. All right. I won't worry about it. All right. Thank you. Thank you indeed. and on and on. Okay, off and on and on. Off and off and off. Good. So what are you doing? Sachi mama. Oh my gosh. Oh my gosh. Oh my gosh. Well, I bid you good night and I see you soon. Indeed. Indeed, very soon. Okay. Is everything still good? Yes. 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 All right. Sachi, come baby. Yes, thank you, beer. See you. Thank you, basket of minks. See you soon. Yeah. Good night. Good night, sleep tight. And if you're joining, please go back to hear all the discussion today for cosmology that we covered earlier today. So feel free to go back in time. Just go to the front of this video and you'll see all our discussions. See you soon. Off and off. Good and good and good and good. Okay. Just shuffling about still. Yes, you guys carry on. Stay as long as you want. Punch each other. Give a few punches to each other. You guys are all boxers, so go for it. And go to the front and listen to the discussion. Thank you. Thank you indeed. Okay. Oh. Come, Suji. cheating.